那个我都拍了。
好，谢谢。
等一下，我还要小心。 比较熟啊。
对啊。
用这个就好了。
对啊，反正就是现在，我觉得就是小的东西
其实就足够
做
用。
到就做得到，就用这个做就好了。
对啊。
我没有想要再刻意再去多弄一个，对吧？
我看那天用那个，你觉得 OK 的话就可以拿来用。
对啊，对啊，我觉得就是这样吧。
我这2天都有在找那个背景。我们可以多抓
我
一些背景。
我本来就有，之前就有先抓了，后来建立。
那你有时候只是抓人物贴上去，贴上日期，就这样子而已。
对，就是把那个图片就是后置处理一下，然后这样就好了。
策略不接受，所以。 因为我知道那个时候可能选那个3元的那个交通费那个，我昨天回到台北之后在想，
好像我今天要去日本，对不对？
也不好意思。
我想，那就是我就是特别早才跟你讲说，应该是。
那我是要直接去付呢，还是说可以就是？
好，那转账是说老师就是有就是 现场有应该有。
或者是说，如果说我们的会这样，
因为那时候没有经过这边做清楚，
应该没问题啊。
对，那
可能会先没有问题，我现在可以开始。
You know, to go I'm disconnected.
都可以啊，如果你方便的话，如果会太多的，你可以在回头关不关？
He just told me that. And that's it. The party function, it's just like the party function is they take that to the over tower. Sorry, take that to the over to the model to the 8th tower plus take the 3 over tower to the that's the 8th tower plus take that over. We basically consider diagonal model. Yeah. Yeah. So I said that the degeneracy is going to count from 64 from the Banning plus 128 fields. So if you got both, you got both on that, what's the thing to get? Give me that plus 9. Same thing. Yeah, but I would like to. Oh, no, yeah. No, it's T4. It's T4 and a special module. Is that a sub-zero? It's not that simple to do. If there's some detail turned on, and I don't know how to describe it. But just do you realize these? If you divide these three balls, and you can just try to keep it on. You can check it out. Who cares? It's not right. It's taken out. It's perfect part. I mean, the one that I did 54 is not appropriately characterized by just Taylor companies. Because generic T4 is.
I mean, you have some other special points. Maybe all those points can be supplied by kind of
No, we know the other some of the other points. For example, also know that the sequence 8. Sequence 8, you only found a scalar that's king and below which you also put an operator. But that theory is the E8 lattice. Gamma. Gamma.
Yeah, but Gamma A was also good. So maybe they are all like, if you guys didn't know, free.
No, but it's not that simple. I mean,
Or they're all
T4.
subdual points.
What you myself do? I mean, the T4 case, there's no example of Mercury factorized. There's 3 characters. It's almost a more factorized than here. The set that is somewhat.
But you also said that there's another sequence 2 space.
And
That means also
self-mirror and self-seal are 2 different things.
over here. Something.
No, no, they're factorized.
Yeah, but that's still mirror.
Yeah.
You can check all this one. The special. This will help you to move like higher sleep.
At the level of partition function, I mean, it's really about the functional entire carbon and natural segment function. Of course, all of these are rational theories that
In some sense, because at the boundary, one of them maximize the decision and for those states,
that is not true. That is not true. It's not true that the boundary maximizes probability. It's more complicated. You mean degeneracy?
It is really.
That's not true. It's not true. Degeneracy is always maximized. No, that's not what I said. What I said is that on the boundary, the degeneracy, there's an upper bound and the lower bound, and they group. But the upper bound and lower bound both depends on the gap. And dependence is not on the boundary. It's generally very complicated. I don't have anything general to say about this. At the boundary, I have the.
This cap is fixed. And the degeneracy is fixed at that point.
The degeneracy also fixed. But this doesn't mean it's maximized. In the sense that if you make the gap smaller, the degeneracy gets bigger. I don't think there's a simple pattern here. In fact, we saw that, for example, in the sequence 1 case, there are many. In the sequence 1 case, a simple example, if you vary the gap between 0 and 1 half upper bound. If you vary the gap, there are several leads. We see several leads. So the pendulum is generally greater than 0. Actually, that's infinite.
What was the 50 more?
Yes. What does it look like? Yes. For large and small cell charts, they're different. So I can tell you roughly what it seems to look like in large cell charts. So this is just say you're doing tau 2, so let me say tau 2 is e to the z, and I write the function partial t. Okay. So tau 2 is e to the z, and I write it in partial. Okay. Something functional looks something like partial z times e to the minus a is partial z. So it has to be opposite. It has to be opposite partial z. Looks like partial z. What possibly is partial z? I'm not sure. So it's like that multiplied by e to the minus a partial z squared. Where a is the number that depends on the electron. It goes like 1 over no, it's just kind of different. The transition is such that modular transformation is close to signal sign. That's the purpose. This was the trying to produce the Hiroshi stable materials. Yeah, so for large C, this trial probably looks like the optimal one over a finite range as our but then it could be switched. The reason this thing doesn't work is that it's currently bounded on the causing frames around the character. What you find is that it doesn't stay the same sign, it will be very large weight. But it has to be very, very large weight, like something crazy. So, if you're not careful, you might be like the range of law, you just use sense to think that this works. It's like almost worse than that. No, we have function parts on it. You see, you can get rid of because how is going to happen? Square. It's one linear. So you just divide it by that. So you have a system that no, it's very simple. Yeah, it's fine that something so simple is hard to do. There's got to be some better. I mean, the thing is that if you're not reading, then I would believe that it's because someone might be surprised that it's like 0 or 10, then I think it's all elementary. Oh, very bad.
Thank you. I'm Koe Hashimoto from Osaka, Japan. I'm a frequent visitor to CTS. I gave one seminar 2 months ago here, but I'm going to talk about a little different story. This is in collaboration with Keiju Murata, who is a KO and he's an activist, and Kentaro Yoshida, who should be seen. Yes. He will talk about a different story. So the topic is chaos. As you may know, the story about chaos has been a kind of gaining interest these days after last year's interesting work by Dasana and Saskin and Stanford. They have given a nice bound of chaos. And my talk is not entirely related to their work, but I'd like to present some new notion of a chaotic index, which can be assigned to hopefully any one of you theories. And the motivation comes from the following. So suppose you ask the following question. This is QCD. And as you know well, QCD is a part of standard model. People are asking why standard model is like standard model. And that's an entire question of particle physics. And we know that the QCD is made of a gauge group, which is SU3. But suppose it is replaced by SU5. So what's wrong about it? Of course, if you know standard model, then there is anomaly cancellation, blah, blah, blah. So the gauge group needs to be SU3. But standard model is just one consistent quantum field theory. And of course, we could have chosen some other quantum field theories that are also consistent quantum mechanics. So the question is why this standard model has been chosen to be our universe, right? And this is a simplified question. So if you actually get a subpart of standard model, that's QCD, then QCD is itself consistent quantum field theory. However, if you replace SU3 by SU5, then that is again consistent, right? So what is the distinction between these two? That's my question. So normally, once you are given some quantum field theory Lagrangian, then you count, for example, what is the symmetry, asymmetry, global symmetry, what is the matter content, and what is the coupling between all of those, and that actually classifies or characterizes the quantum field theory. And I want to add one more index, which is a chaos index. Maybe this is helpful for phenomenology in the future, but I don't know. So in this talk, I'd like to concentrate on this kind of question. So suppose we have two different actions, like this, then which is more chaotic? At first sight, of course, you say that SU5 is more complicated, since you have a 5 by 5 matrices, so the degrees of freedom is larger compared to SU3. However, the thing is not really like that, since we know that quarks are confined, and we never see countless degrees of freedom in nature. So the comparison between SU3 and SU5 is completely quantum. If you look at this system only by classical action, then of course you would say that SU5 is more chaotic and complicated. However, the question is not that simple. Okay. So now we know that these are written by Lagrangians. So this is Riemann Lagrangian. This is also written by Lagrangian. And Lagrangian have different parameters. And the chaos example, one of the famous example is this. This is a double pendulum. So we have two mass points like this, and they are connected by rigid rods. And this has a Hamiltonian for Lagrangian. This has also a Hamiltonian. But the parameters of these Hamiltonians are slightly different, since I specified the length of these rods. Okay? And we can actually know which one is more chaotic. So let's look at this movie, which I created by using Mathematica. It's an easy code. If you can Google double pendulum Mathematica, then you can get it. It's easy. So the left-hand side it goes like this, and the right-hand side goes like this. Okay, then could you recognize which one is? It's really know that it's chaotic since it's a double pentagram, it's a famous example. However, dependence on the parameters, that's the most important part. Right? So this is the story. So first I will tell you, this is a review, section 1. What is chaos? This is a very introductory and quick review of classical chaos. In a word, chaos is insensitivity to the initial or very precise sensitivity to the initial condition. Suppose you change the initial condition a little bit, then the outcome can never be predicted due to this very small change. It's called butterfly. And then in section 2, I'd like to consider effective low-energy model of QCD. So usually we only rely on some symmetry breaking patterns and something for physics. So this effective model, which is known as a linear small, is the most popular effective model in QCD. We show that it contains chaos. But this is just an effective model. So how do we treat this QCD? So in section 3, I will use ADS-CFT. So if you use ADS-CFT, then QCD is in the CFT side. You can take a gravity dual. That is a classical gravity. So you can use classical chaos technique or some sort of supersymmetric QCDs and check whether it has a case. So this is the virtue of it. And finally, I'd like to discuss only by one page what is the relevance of our result to say what mathematical result and other chaos like holding black hole entropy and so on. So please stop me anytime if you have a question. Let me start with the review on classical case. So what is classical case? It's simple. This is a copy and paste of Wikipedia. So you or any text of chaos. There are many nice textbooks on chaos. So it is a non-periodic bounded orbit, sensitive to initial conditions. Okay? So that's it. So if you slightly change the initial function, then the outcome reverses quite drastically. So it has a very long history. If I look back, then there is already Poincaré's grounding work about the observability of three-body planetary system. So if you start with Newtonian gravity with 3 stars, then the motion is chaotic, and there is no analytic solution for that. That was from the bodies. And then in 1963, Lorentz showed a famous, so in his famous talk, he considered an atmospheric model of our Earth. And then he referred to kind of butterfly effect. So suppose butterfly flies in some city in the US, then it will cause some hurricane or typhoon in Asia. So that is a drastic change of the result, even though the initial condition is slightly different. And after that, this Hamiltonian system has been studied quite intensively, and this is a nice example. It's called Greenberg Beach VF4. Suppose you have 2 different positions and starting point, and this here study is very simple. It's parallel lines plus half circles, and that's it. However, you cannot predict the motion. So this is a famous example of chaos. And now, what about quantum field theories? So of course, quantum field theories are difficult, so people try to consider classical Lagrangian. Since, for example, the Yang-Mills classical Lagrangian equation motion is nonlinear, so it exhibits some chaos. And Savigny and Mueller and all of those people worked in the 1980s, 1990s, and they found classical chaos in those classical
But that's true just for scalar matrix model, right? Right for it, right? Nonlinear Mills.
So this part.
Yeah.
Yeah. So what? Yes, that's a good point. So what Mueller and his collaborator did after 10 years of grounding work by Savigny is that they consider a lattice model, so in space. And on the lattice, you can put this classical Yang-Mills, and then they that's point. So in that sense, let's say the vector notion of Yang-Mills can be implemented in the lattice structure of space. And of course, there are lots of applications like information theory, and I think I don't need to tell all of this. But there are many subjects in scales theory. So I'm going to tell you two important notions of chaos, which signifies the chaos for a given system. So one is the Poincare section, and the other is Lyapunov exponent. So what is yes?
So suppose you can show SLC or say something chaotic, but then what do we learn beyond what we know about the QCT concept? Presently, what do you add to our present knowledge?
I think that's the most important question, and I don't have any answer. So what I show is QCD has a chaos, and that's it. How important, how it should be applied to other aspects of QCD is it's an open question. So I explained two notions. One is Poincare section. So suppose you have a Hamiltonian system, like a motion in some Hamilton state or something, or potential. And this is a motion in phase space. So it's X and P space. And you have initial function here. And if you put the initial function here, then it moves in your phase space. And Poincare section means that you have a section in this modular state, in motion space, phase space. And then plot the points which intersect with this motion in space. And collect all the points. And this is a result of double pendulum. So of course, it depends on the initial energy. If you put a small energy, then the pendulum is has a very regular motion like this. So the Poincare section looks like this is a collection of points, and it's regular, and it's called compound. However, if you increase the energy, then the Poincare section has a scattered plot like this, and then the large energy it covers all the space. And from this, we say that the motion is chaotic. And for that, it's not chaos. So the chaos is indicated by scattered plot of Poincare section. And another notion is called Lyapunov exponent. So this is very it's matching the intuition of chaos. So this is phase space, and this is the trajectory in phase space. Suppose we change the initial condition slightly to this. The distance is given by d at t equal to 0. And if the system is chaotic, then the motion in phase space is separated by this, and the distance in time t is exponentially separated from the origin. And the coefficient L here is called Lyapunov exponent. And if Lyapunov exponent is positive, then it means that these are exponentially separated, so you have a chaos. On the other hand, if this L is 0, there is no chaos. The positive value of Lyapunov indicates the chaos. And this expression is just a rewriting of this expression in a more precise way. So let me go back to the examples of double pendulum. So this is the left double pendulum. This is the right double pendulum. And if you look at the Lyapunov exponent, then actually this is bigger than this for fixed energy. So this concludes that quantitatively, the left double pendulum is more chaotic compared to the Any objection? Good. Yes, question.
Can you prove this relation of some class of theory, or is it possible to have LT squared for the
Or is
do you have any example which not like this? Doesn't follow this?
Yeah, of course, if the system is regular, I mean, the system has no chaos.
So we need more.
And yeah, this should behave like a power. And exponentially is bigger than power.
Okay.
So in that sense, this positive L indicates.
We can do something more chaos.
I have no idea about that. Yeah. particular, I think it has been proven that there is no such system for a class of Hamiltonian systems. I don't know if that's what it is.
You already showed one space dimension case. The dimension is important or not important?
It's very important, yes. Thank you for the question. So for this double pendulum, you have 2-point particles. So the phase space dimension is 4. So 2 plus conjugate 2. And if you have only one point, then it is known that there is no phase. And it's called Poincare-Bendixson theory. So you need to have more than 4 degrees of freedom in phase space, or equal. And this is the simplest case. So if you go to field theory, then field theory has infinite degrees of freedom. So it actually satisfies the assumption of Poincare-Bendixson theory, and the issue is how you reduce the system to calculate this.
So that Lyapunov exponent depends on the energy?
Yes.
So you can show that the left pendulum is always more chaotic than the right one for every
Right, but so the truth is that I just adjust the zero of energy, so as I mentioned, low energy there is no chaos, and the distinction between these, so there is a threshold energy, and this threshold energy of course depends on the zero of energy. So you can assign this zero of energy so that these two have the same threshold, and then you can compute them. That's how. Okay, so these are classical chaos, but you can ask what is a quantum chaos since QCD is quantum. And I just told you that QCD Lagrangian itself doesn't make sense since psi is Q is core with a fermion. It doesn't have a classical expectation value, so what do we do? So in fact, there is a very long history about confusion of quantum chaos. Normally quantum chaos is defined as quantizing classically chaotic systems. So it doesn't mean anything new about quantum chaos. But what is known is that once you quantize the classically chaotic system, in the energy spectrum of this system has a nice distribution. That is a Wigner distribution. So this picture is an atomic energy spectrum of lithium under a constant electric field. So this is the electric field, and this is the energy levels. And first, it has a very degenerate energy spectrum, since the angular momentum and such are inert. However, if you increase the electric field, then they align almost like equal spacing. And if you plot the statistics of these energy levels as a function of next to this spacing of the energy levels, then it looks like this. So this is the spacing. This is how many you have as for energy levels. Then it has a peak around. So it means that it is almost equal spacing. If you plot this for non-chaotic system, then it doesn't work. It goes like this just for some distribution. So there is a proof, almost a very nice proof, that once you quantize the system which has a classical chaos, then the resultant energy levels are Wigner distribution. Okay. But unfortunately, the notion of Lyapunov exponent, which is very important for us, how sensitive the system behaves classically, is completely washed out. Since the Lyapunov exponent, if it is positive, then it's chaotic. Then you quantize it, then you have a Wigner distribution. But once you get to Wigner distribution, then there is no notion of Lyapunov exponent. In quantum system, the Schrödinger equation is linear. So it's just a time equation of liquid. So how can we define how much the system is chaotic? You can know system is chaotic, but how much is this chaotic? That is the question. So the issue comes to this quantum versus classical. So I'd like to address that question in section 2. I come to So let me argue the system by using effective model. QCD is, as I said, it's truly quantum. So suppose you have both an anti-quantum, and they are confined by quantum effect. and form mesons. Say, for example, in a single flavor system that for simplicity, Q bar Q is a meson sigma. Q bar M phi Q is a phi. It's a notable for modes of chiral symmetry breaking. And furthermore, quarks are condensed, and that's why chiral symmetry is broken. You have Q bar Q, that this is chiral condensate, or chiral condensate. That is known to be non-zero at zero temperature. And this is the reason why the chiral symmetry is broken spontaneously. This is a chiral symmetry. There is a chiral coefficient parameter. Q is loaded by M5. Q bar is loaded in the same manner. So once psi upside this expectation value is non-zero, chiral symmetry is spontaneously. Okay. So what is the effective model of QCD? If you look at the graduate school textbook of QCD, then it starts with this linear sigma model. So this is a linear sigma model. We have sigma and pi mesons and potential term. And it has a mass term, it has an interaction term, and it has a constant to adjust the zero mechanism. And furthermore, there is this kind of term. So what is this? This model is known to describe QCD upload energy. With, for example, in the case of one flavor, if you ignore the anomaly, then this diagram that describes QCD. If it is two flavor, you can consider anomaly 2, but if you ignore neutral final sector, then that is U60. So this is a nice model of QCD, don't you? Why? Since this breaks the U1 symmetry spontaneously and at the same time explicitly. So what is the spontaneous part? If you look at this part, sigma and pi, this is a complex scalar and complex square magnitude 4. So this is pi 4 model. So if this mu squared is negative, then you can say that this model has a spontaneous symmetry breaking of U1 potential symmetry in sigma pi space. So in this picture, this is sigma direction, and this is pi direction, and this is B. And in addition to that, we may have this term, A is a constant, A times sigma, and that explicitly breaks the U1 symmetry. Since in normal QCD, if it is massive, then if quarks are massive, then there is a quark mass that is A times Q bar Q. So effectively it induces this term, and in the presence of that term, the U1 axial symmetry is broken explicitly. The effect of this term is to tilt this potential space. And there is a bottom here. And bottom has a non-trivial value of sigma expectation value, and we know that this is equal to final decay constant. So that's how it takes the process. Now, interestingly, this potential has the analogy to the double pendulum. So this bottom is of course corresponding to this, that is this one. However, there is a special point here, around which if you tune the energy, then the motion becomes very, very small. So suppose you have a motion in this potential, and put some initial condition and move it. Then if the energy is tuned to be the height of this part, then the motion becomes very, very slow. And if it becomes slow, then it forgets about the initial condition. And that is why double pendulum has a chaos. So if the motion looks like this, if the energy tunes here, then the motion here becomes very, very slow. So it forgets the initial condition. So this resembles quite much the double pendulum, and it is known that this part is called matrix that induces chaotic motion. Okay, so once we know, we expect that there should be chaotic motion in the system, and we can look at, say, Poincare section. So to fix the coefficient in the model, of course, you can use some experimental values, like a pion mass is 100 kilogram MEV, and decay constant is that, So you substitute those experimental values to the model, then coefficients are completely fixed. And then you tune the energy and write one section. If the energy is not so large, it was only a regular motion. The difference of the colors is just the difference of the initial condition. So depending on the initial condition, the motion in this counter section defined by pi equal to 0 in the space of sigma to sigma dot base space. Looks like a nice story. But if you change the energy and increase the energy, then some of the tori collapse, and then you can become scattered apart. But eventually it goes back to a regular motion and high motion. So around the energy of these tuned separate groups, you can actually observe chaos in the world.
So here your question is homogeneous.
It's homogeneous.
So it's what the equation you can realize. Classical homogeneous motion.
It's an assumption. Yeah, it's an assumption. Yeah. So thank you for a very important question. So in the analysis of chaos of field theory, first you need to reduce the number of degrees of freedom. Since if you have infinite degrees of freedom, then you have no way to analyze this. So we need to regularize the system. And the simplest one is to assume the homogeneity. However, you may ask, okay, this is only for homogeneous system. What if you have many more degrees of freedom? Then the thing is that empirically, what we know is that once you have chaos in homogeneous system, then even though you increase the number of degrees of freedom, normally chaos remains. It's just empirical. For example, in the case of Yang-Mills, Yang-Mills classical equation motion, we so Savidi first analyzed that in homogeneous manner, and then Müller and collaborators put that on a lattice, and then analyzed quite a similar manner, and then found that case. So yeah, it's just an empirical fact. But to reduce the number of degrees of freedom by assuming homogeneity is one empirical way to find chaos. But there is no other good reason. So for example, if this situation can realize in the early universe, I have no idea.
You can have a two-field inflation model, something like this.
That's right, yeah. So in any inflation model, so normally to simplify the model, we assume the homogeneity of impact of the field. So, but it is not just, it is about the initial function problem of cosmology. So here it's the same. We just assume to get extra information.
You switch of loop corrections.
So here the notion of loop correction is very ambiguous. Since I started with the low energy effective theory, what do you mean by loop correction? Loop correction of sigma model? Yeah, of course you can include that. But the problem is that these numbers at this stage, these are nothing related to QCD parameters. So I have just put the experimental values for these things. So even though you could compute some loop correction, I don't see good motivation for it at this stage. Yes.
Unrelated question. So if you have some field theory and you have solid group, so the chaos can appear inside minus it always appears when
yeah, I think that's a very interesting question. And for example, for this, for the case of Yang-Mills Higgs system, which has been studied in 1980s, 1990s, they introduced, for example, monopoles there, and whether the chaos changes or not, they check. And the result is that once you introduce those monopoles, for example, and chaos is enhanced. Yeah. So that is an example of a particular system. But the introduction of soliton includes spatial inhomogeneity. So the direct comparison from non-soliton case and soliton case is really important. But for this case, we know that there are experiments, so the relevance of experiments is important question. So since we knew from compound section, there is a chaos, so you could check the Lyapunov exponent. And this is one example for a fixed initial condition. At low energy, there is no chaos. This is all numerical computation. It's zero. But there is some threshold energy for fixed initial condition. Then you go to high energy, it is terminated. So around this area of energy, there is chaos. And yes, please.
Do you know what happens when you gauge the sigma model?
I have no idea. However, we could expect that this chaos remains. So as I said, normally, once you have a chaos in this subsector, then it is difficult to eliminate it by adding some more units. So that's an intuitive answer. But I think that's an interesting question. So one observation is that this energy scale with the non-zero Lyapunov exponent coincides with QCD phase transition energy. I don't know why, but there may be some relation between this Lyapunov exponent and QCD phase transition at the finite temperature. There may be some relation. And in fact, I'd like to discuss at last that once you have Lyapunov exponent, then there is a way to define information entropy from Lyapunov exponent. And that entropy sometimes coincides with thermal entropy. So the notion of phase transition at finite temperature, which is very important in QCD, could be related to this classical analysis of sigma.
So is the mass of the pion can 130 something?
Yeah. This is yes.
But what about 170?
I don't know. This is just a numerical result. And what I could say for sure is that the energy around here is really close to the height of this separatrix in the potential. So we could definitely say that this separatrix generates chaos. But the difference from QCD phase transition is that, well, QCD phase transition occurs even for massless forms. But this one doesn't occur at the massless form. Since the mass of the fork is relevant for the field for the potential. So the reason why we have phase transition is actually hidden. Maybe this may be related to QCD phase transition, but I'm not sure. So this is the end of the section 2 story question. So let me go to ADS-CFT. So until now, we worked in linear sigma model, and that is an effective model which specifies how symmetry is broken spontaneously and explicitly. And of course, we are not really satisfied since the coefficients appearing in the model is just like experimentally fixed. But we truly want to consider the question. The question is QCDs with SU3 and QCD with SU5, which one is more generic? And for that kind of question, we could resort to ADS-CFT. Of course, we have to change slightly the question. For example, we need to take Gaussian limit, and also we need to take strong coupling limit, but it is still truly common. So what is the meson theory which can be calculated from ADS-CFT? So this is the result. So you have two kinds of mesons. It's phi A, so A is 8 and 9. You have phi 8 and phi 9. Those are sigma and pi. And here, for simplicity, I consider two flavors. The last example was one flavor, but this is two flavors. And what is the classical action deduced from ASCFD? So this is gravity side. You have two mesons, and you have mass terms for the mesons, and also you have interaction terms for the meson. And this interaction term is commutator squared. And of course, this comes from a kind of dimensional reduction of inductive theory. So this is deduced as an effective action of a probe grain in AS. So what is the theory of it? It is a theory of mesons in N-equal-2 supersymmetric QCD. And the meson masses were analyzed by many people, in particular first by Rutensky, Matheus, Myers, Winters. And this theory includes Yamnon's gluon sector plus N-equal-2 for hypermorphic spread. The parameter of the theory is optical coupling, colored FC, and focus. So let me remind you of how this was derived. So supersymmetric QCD has strong coupling limit. It is of course periodic order. So the normal classical analysis of case doesn't work. However, if you use ASFT, then you can map this system to classical probability. So this is completely classical system. You can do 3-level analysis, and that corresponds to completely quantum spectrum of supersymmetric QCD. So this is the virtue of ASFT for chaos. In chaos, as I said, quantum chaos is a vague notion. Classical case chaos is definite notion. And there you can define how much the chaos is. That's the Yakoff exponent. The problem was QCD is very quantum, so how do we do? We could need to take a classical limit. But normal classical limit doesn't make sense. H1 goes to 0 doesn't make sense since forms are fermions. However, if you take a ASFT and it goes over to classical where co-condensate exists.
Could you say this special reason why you take the two flavors?
Yeah. So since this is supersymmetric QCD, at 3-level analysis, I couldn't find any chaos for one flavor.
For more flavors?
For one flavor.
For one flavor, but why don't you just take a flavor to be arbitrary but in a probe limit?
Yeah. Yeah. So the reason would be kind of obvious. Here, at the leading order in lambda minus in 1 lambda, you have this calculator term. These indices refers to flavors. Yes. If you have only one flavor, then there is no term like this, and it's free.
Right, but why don't you have more flavors? That's what I'm wondering.
Well, yes, we can add more flavors, yes. And chaos is there.
It's there, okay. It's not nothing to do with like you have to compare the lattice simulation like you do.
No.
I was wondering about that.
It's
Okay.
But that should be. Okay, if you look at this thing, then as I said, this is a kind of dimensional reduction of the diagonals. And you can reduce this system to a homogeneous. Yes, please.
So if we include the one-to-one correction things, it becomes front. In a program application.
Yes.
Doing one-to-one correction, then it becomes front. So we cannot define K as classical K systems. We have nothing response. So your result only valid for strict agenda.
I think so. So we could evaluate, for example, one-to-one lambda. One-to-one correction is a quantum graphical stability, but one-to-one lambda correction could be, we explicitly evaluated that. And for that, we could check whether the chaos remains or not, and the result was positive. But one-to-one correction is. So I'm asking, the question is the dependence on MC, but this is very, very large. So if you say that MC is infinite, then I cannot compare it. But what I will do is to compute the Lyapunov exponent of this thing as a function of MC. So okay. We can do the analysis, but unfortunately, this system has been already studied in 1981 by original paper by Savity. So he was looking at the YAML's Git system and dimensionally reduced that to one dimension, that just type correction, and consider the YAML or configuration upon section. And we noticed that the system is exactly YAML's Git system. Eventually, since our action is this, and if YAML is dimension reduced to one dimension, then that's it. So we could actually borrow their work. And what they did is, further to reduce the degrees of freedom, you turn on only sigma 1 component of 8 and sigma 2 component of 9. And that gives you a decoupled system of consistent truncation integration motion. Then these coefficients elsewhere are G in terms of this X and Y is given by this. But the point is that compared to the previous linear sigma model, you notice that here G and M are explicit written by QCD variables, C, lambda, and MQ. So we could tell you, we can tell you what is the dependence on MC and lambda. Okay, so let's do the analysis. Here is a pointwise section. The unit is chosen to be Cognes, so Cognes. This is for numerical simulation. I just took these numbers, and you can do for any numbers. At low energy, there is a regular motion. But if you increase energy, then some of these control graphs, and you got scatter plot. So this means that at higher energy, it's a chaos. And you can also do a computation of the Lyapunov exponent. So let's look at this next figure. So this is the Lyapunov exponent L versus MC. So this means that if you increase MC, then the Lyapunov exponent increases. So effectively, for smaller MC, the things are more chaotic. So that's the reason. But one comment is that here I put an interesting prefactor here and there. The reason is that there is a scale invariance of the equation of motion of this system. So there are two scale invariance parameters, alpha and beta. And the system doesn't change if we do this scale transformation. And these combinations, this one and that one, is independent of this scale parameter. So that's why we chose these combinations as for the problem. On the right hand side, we have plotted this Lyapunov exponent as a function of sampling time. So it shows an interesting behavior. Here there is 0, but there is phase transition around here. I increase this energy for equivalent integral time. Then you have a linear behavior here. It is described by a very strange formula. I have no idea how we should interpret this, but it increases and then it goes down. So this is a kind of experimental hit of what is calculated as for Lyapunov exponent. But the tentative conclusion here is that for super QCD, meson sector at large N and large lambda region, for smaller MC, okay.
Sorry. There are many, infinitely many coordinates. But then you assume these shows the same.
No. That's a very important question. So in quantum field theory, what you want to measure is actually infinite number of possibilities. And this one is only for meson exploration. Since we know that QCD is characterized by Q bar Q. Of course, there are many other operators.
For example, you said it's a small NC, it's not big, but they
sure.
But maybe some operator shows it.
I have experience.
So it's
Yeah. So this, of course, this analysis is only for higher conditions. I hope I could do some good argument of some other competitors. But I cannot. So what I can do is just use supersymmetric transformation. And as for operators which can be related to this kind of condensate, I'm sure that I will make the similar. However, since we don't have more symmetries, I have no idea about this. Okay. So I'm going to finish just by one page, the discussion part. So there are interesting possibilities for the new directions. So there are three things I just listed: pornographic principle, entropy production, possible application for phenomenology. I'm not sure. So how about pornographic principle? As has been done by Yoshida-kun's work, for example, once you find a chaos, then it means that integrability is lost. So it is important to find a chaos in expectedly integrable systems, like a BMN model. Yoshida-kun has shown that there is a chaos. And so integrability is very important in our setup. However, the chaos is on the other side. So it's just And also, Hawking argued recently in 2014 by his just short two-page paper essay that the black hole information loss could be a butterfly effect. Maybe you know that paper. It's very short paper without any iteration, and he says something which is mysterious. However, the important point is that the chaos can be implemented quite nicely by classical quantum duality. So once you have a black hole in a side, then I hope, I expect that the chaos is enhanced by the presence of a black hole. Then that could be replaced in terms of finite temperature, QCD, or something like that. So the black hole and information loss is related to chaos, and how that picture can be put consistently to this kind of picture is an interesting question. And finally, as I said at the beginning of my talk, there is a conjecture upper bound of chaos by Mandasian and Simon Susskind, where if you take a classical limit on that, then the bound becomes infinite. It's bound up. It is a bound up at Lyapunov exponent. The conjecture is very simple. The Lyapunov exponent for any theory is bounded from above by temperature divided by h1. So how this conjecture is might be consistent with our analysis is a mystery. Mandasian and Stanford Susskind considered a very special operator, which is called out-of-time order operator. And for that kind of operator, they conjecture that there is a bound. But how about other operators? That's an open question. And also, there is an interesting relation between these two things. So Mandasian and his problem, they found that this bound is saturated when you have a black hole beyond. So a black hole is responsible for saturating this bound. That's very interesting about. So how about the entropy flux? So how much do you have? Few minutes. So how about entropy production? As I mentioned in the linear sigma model case, phase transition seems to be occurring at the same energy scale as the Lyapunov exponent was. And phase transition is, of course, a thermal entropy production if it is a first order phase transition. And it is known that the Kolmogorov-Shinai entropy, which is defined by the Lyapunov exponent, is in a Y-class of Hamiltonian system is equal to Shannon entropy rate. And this Shannon entropy rate is discussed to be equivalent to thermal entropy. So there may be some hidden relation between this Lyapunov exponent and phase transition study, but I'm not sure. And people in Kyoto University, in Kyoto collaborators, sometimes they do the first paper. They discuss thermalization of heavy ion collisions and very rapid entropy production from Yamil's case. And that's an interesting trial. However, the result seems not convincingly reproduce what is known in experiments so far. So I think the relation between classical chaos and entropy production would be quite interesting. And at last, I'd like to discuss phenomenological thing. For example, if you look at the recent developments on Higgs radicality and Higgs inflation, then the potential they draw in the paper looks really similar to what I have shown, the linear sigma model. They have a separatrix, and our universe is sitting very close to the separatrix. We don't know why. And also, there is a scenario for neutrino masses and mass matrices, and those are called Aranaki scenario by Haba and Hayama. Why mass matrices are found to be chaotic? That's a question. And people criticize this Aranaki scenario as a non-predictable theory of neutron masses. However, there may be some reason why this is chaotic. So these scattered questions in phenomenology may be possibly related to chaos at the strong coupling limit, and I'd like to happy to discuss these things. Okay, thank you.
Would you say something more about the upper part of the field? Is it upper part of the about the exponent?
Yes, it's the upper bound for the actual exponent. I don't remember the condition, but it says that the exponent is a temperature. And temperature of the field, total field. So if you are discussing the normal classical chaos, then you need to take h bar to 6. So it means that for a very slight temperature, it is things close to that temperature. There is no bound. So their issue is how about the quantum case with the temperature. And of course, as Akirashima-san notified, this L depends on what kind of operator. And they proposed a special set of coordinates. It's a 4-point coordinate that includes time differences. So two operators are put separated from the original one by time. And then for that class of operators, they argue that. And the interesting thing is that, so if you want to interpret this from a holography, then Lyapunov exponent, that is a chaotic index. So it means that how you lose the information. If you think of this as an entropy, then entropy grows, then the information is lost. So this measures how much you lose information. On the other hand, if you look at ACT, then final temperature means that there's a black hole and it grows. So the area which you can see as an emergent spacetime is limited. So this has such kind of holographic understanding, and that is really intimately related to, say, recent developments of how information theory can reproduce the emergent spacetime.
I mean, measure the boundary field is not just Minkowski. And the definition of the uniform scale is actually dependent on how you choose the time.
That's right.
Yeah. This is probably still not general covariant.
Sure. Yeah, of course. So it's related to the next talk by Yuval Gentry. So if you have a logical QFT, then it has another function in cosmos horizon itself. So this kind of equation for inequality can modify the case. I think that's how it is.
So, in your setup, if I understand correctly, then, does that mean your inverse of the Lyapunov exponent is basically the QCD phase transition system?
Well, it is an observation, but as I mentioned,
But and also, okay, that's I just want to know whether this is the artifact of your setup, or was it because there's some other reason to understand? For example, later on, you make this final statement about this Shannon entropy, and is that directly related to QCD entropy, or is there some other way one can really nail the statement that the
no, it's
inverse
not
is?
shown.
Okay.
So what this entropy rate could be related to thermal entropy is really restricted class of Hamiltonian systems.
Right.
So of course QCD is a quantum field theory.
Correct.
So nobody knows whether this equality is at all.
Or is there some effect in Lagrangian that you can derive from RT flow QCD or some other cousins?
Well, I agree that that's an interesting question, but
that's not
at this stage I can go ahead. Yes. So the chaos, so for example, classical chaos quantize becomes a Wigner distribution, and only for that proof, it took I think 20 or 30 years to get to the proof. So yeah, for this entire project is really big questions. Yeah, that's my.
So your result on SQCD actually has very little to do with supersymmetry.
Sure. Yeah.
So basically, it has more to do with large NC.
That's right. So that's why I'm working on non-supersymmetric version of QCD for dividing using ADCD. Yeah. So here the model here. For example, the chiral condensate of this theory is C. So that's why for the one flavor case there is no chaos. But in a non-supersymmetric case, of course, chiral condensate is not.
But even in the case of a linear sigma model that you talked about, there is a well-defined, there's a huge literature trying to use ADS-QCD to compute.
Sure.
And again, if you do the same thing for a linear sigma model, I really think you will find it exactly the same.
Yeah, I agree. Yes. So we are working on that. And as you say, we expect that that will be the case. Okay. No more questions? Yes, thanks.
因为 Y 在这边啊 ，Y 左边这条线啊，测定线不会这样啊。对啊，如果你想想看，如果这两只线交叉的话，它不会走到这里是最短，然后再走到这里是最短，然后矛盾。因为它最短是有一条，就是这样子。以后 下面就是下面这个就是把它拆掉。
或者说做一个也是要做那个我们那时候在想说，中间可以换。因为我自己在想，
没有两方就可以操作。然后这个一样的时候，这边一样的操作就有想，就是下面这个口机。
With what?
This is not
Oh, wait, you said there's a marginal. What is the value of this marginal?
so this x cubed plus xy
Plus x times y. And plus z cubed.
So that's the first two monomials here.
And the deformation?
Deformation is like, no, it's just, for example, y cubed.
Dy.
I think analogy right, it's related to the look at the deformation.
Yes, it is.
And look at the one cycle before.
Okay.
How it changes the circle.
So, do you know what the space looks like?
Yeah, because if you take the zero, that makes a zero.
Okay, let's start our second talk.
Okay, so it is on ADS and the sitter correspondence, on ADS CFT. This is somewhat that we have done in the past with some standard German and some work in progress. So this is the outline of my talk. As usual at the beginning, I will introduce and I will say some things for the setup of the space, and I will motivate a bit the study. And then I will move on with three computations. I will avoid, obviously, very hard technicalities, but I will show you how we can compute, in this case, field theories that I have on the de Sitter space, the entanglement entropy. Then I will tell you a little bit about the energy of the quark bound states, for example, of loops. And then I will say some things about the bulk-to-boundary formalism from ADS-CFT and how to compute two-point functions. But then I will just summarize. Okay, so let me introduce the study. The first slide is very basic. So the ADS, the Sitter are Einstein spaces, and we know that there are solutions of them space Einstein equations with negative important logical constants. So you take the Einstein field reduction, which looks like that, and you know that it has maximally symmetric solutions. So these solutions, they have the Riemann tensors and the Ricci tensor that they are proportional to the metric. And in particular case of these ones are the ADS metric, particular symmetric case, symmetric space, maximally symmetric space, that in the Poincare coordinate satisfies takes this form. So here is, let's say, my space-time, here is my radial coordinate. If I take z to 0, this is my boundary of the space, and this is that Minkowski boundary. Okay, this ADS space happens to be a solution of the two-disk spectrality. In near horizon limit of T3 planes, of course supported with some fluxes and some internal space, and this motivated the top-down ADS-CFT correspondence like Feynman descent. Now, instead of having a de Sitter Minkowski boundary, I can take a de Sitter slice of a de Sitter space. So my boundary now, I can set the boundary to the de Sitter space. How do I do that? I take the de Sitter space in D plus 1 dimensions. This is invariant under the SO 2,3 group. If I take a Lobachevsky-like embedding, this is a D plus 2 constraint. This is the radius of the space. And the similar constraint holds for the de Sitter in D dimensions. This is invariant under the SO 1,D group, and this is this Lobachevsky-like constraint. So here, both of the radius are equal to R, and the only difference between this and this embedding, the constraint, is the 2 minus sign. Now I can take the de Sitter slicing of what de Sitter space just by hyperbolic parameterization. So here I am taking these coordinates to be parameterized like that, and here I am taking the space coordinates to be parameterized by hyperbolic sign. Now why I am here is just the constraint that appears in the Lobachevsky embedding of the Sitter space. Now if I do that, and if I find the metric, I will get something that looks like that. So I haven't specified yet what are the coordinates of the de Sitter space-time, but what I get here is the radial coordinate that is outside, and here in the metric I get a hyperbolic line and the de Sitter space. So by taking the radial coordinate to infinity, I'm having a boundary that is a de Sitter, instead of having a Minkowski. So this is the space that I will be using from now on. Now here, as you see, I have a freedom of what coordinates I will take for the de Sitter space. And there are several choices. Every time I will choose, I will pick up the one that is more appropriate for the computation I will do. So there is a non-planar coordinates. This is a parameterization like that. So here are the exponentials, and I have this 0 and d components, and they have sine and cosine parameterization. If I do that, I will get the metric that looks like that. Now the cosmological horizon is the inverse of the radius of the space, and I get a space that is expanding with exponential rate. Okay. So here, for example, this looks like that. Here are the blue lines are my geodesics. If I put, let's say, 2 particles here, the geodesics diverge from each other as a result of the expansion of the space. And here the black lines are the constant time sliced. Of course, I can write the space in terms of conformally flat and the conformally flat coordinates, and it looks like that. Now x0 is my time, and I can write also the space, the de Sitter space in the static coordinates, which is a little bit simpler because I can see a time-like healing vector in this metric. So then I can see also a presence of horizon, which hints the thermal bath temperature. Now here the space looks like that. The time direction is like up here, it goes up, and here is my geodesics that they have now equal distance. So I have 3 different choices that I will be using in this talk. Okay, so since I'm in Kev space-time, I have to define some quantities. Basically, I will compute observers, so I have to define the distance between the 2 endpoints. Just a small comment here that de Sitter is free from singularity. So if you compute invariant scalar quantities, they will be free from singularity. Like the Kretschmann scalar here, you find it doesn't have any singularity. But what is more important here, for the next talk, is that I want to define a geodesic distance in the ADS space. So this geodesic distance will measure the distance on the boundary of 2 points x and x prime. So in my slicing, if I compute the geodesic distance between n, x, and x prime, 2 different points, but they sit in the bulk, I will find this formula. So you see here that still I don't have to specify yet what is the de Sitter coordinates, and I have only the radial coordinates and the space-time coordinates in a different in a different expression. And then if I specify my expression, for example, in the planar coordinates, the geodesic distance between the two points at the boundary takes this form. Okay, so this is something that we will use from now on as a distance between two endpoints. Now, of course, sometimes we may want to compare with the flat space-time. So we can define a new quantity. I will define this geodesic distance by just rescaling this p here and adding a -1, so that at the flat space limit, when I will take the cosmological horizon to 0, or the radius of radius of the Sitter space to infinity, I will get the geodesic distance equal to the one from the Minkowski space, just for convenience. So this one from now on, it will be my distance of the two endpoints at the boundary. Okay, another side remark here that is also important is that this theory is on curved space-time, so it does not have a unique vacuum. So if I, for example, I consider the two-point function in the de Sitter invariant state, I know that to base the Sitter massive star equation. Now I know that this invariant state, so I can make a very nice here coordinate transformation, and this complicated differential equation I can bring it in terms of one only derivative, so like an ordinary differential equation, where is only the invariant distance between the two endpoints. So if I solve this equation, of course I will not show you all the solution, this is quite known, I will get some hypergeometric functions, and there are two linearly independent solutions, one with plus PDS and one is with minus PDS. So this defines a one-parameter family of the Sitter invariant vacuum states, and only for one particular constant of these solutions, I will get the Bunch-Davies Euclidean vacuum. The vacuum that is a canonical choice, and that corresponds to when I take the radius of the de Sitter space to infinity, I will get the flat vacuum. So this is the canonical choice, and this is the one I will be using from now on.
Okay, excuse me. For massless case, maybe construction of the de Sitter invariant vacuum is quite non-trivial. You always put mass?
Yes, I will have mass.
You do not push the massless case?
Oh, the theory is massless. The theory is massless.
So here I have the Sitter massive star equation.
Yeah,
in this case.
Our theory is massless.
Yeah. But this one is.
So you do not take the n equals 0 limit?
I will just show you the computation. Okay, so let me just coming to this question, I will just now directly go to compute the entanglement entropy. So here I am taking, here let's see the setup. Here I'm taking a given time slice on a time slice of the de Sitter space, and I pick up a closed surface. So then if I pick up a closed surface, then I can approximately decompose the Hilbert space on the modes that they are inside inside this closed surface and the modes that they are outside. And then you can define the density matrix by tracing out all the degrees of freedom that are outside this closed surface. And by defining the von Neumann entropy, you see how the degrees of freedom inside this closed surface are entangled to the degrees of freedom that are outside. So basically, this is the entanglement entropy definition. So in the particular case, for the four-dimensional de Sitter space, the entanglement entropy takes this form. So here, let's see, it has two different parts. So here, this is the UV divergent part, and this is the UV finite. So you see the epsilon is the UV regulator. So here, this term, all of these terms, they have a particular origin. For example, this term is known to come from the degrees of freedom, from the modes that are around the boundary of the surface with area A. This is two terms that they appear in the flat space, and this is one term that appears in the de Sitter space, and it has a connection with the curvature of the space. And this is the finite terms that they have similar origin. Now, Now the people, now in this paper, some years ago, the people managed to compute, to isolate and compute this logarithmic coefficient here. So they took a free massive scalar field for a spherical entangling surface, and they have computed this constant in terms of this quantity here, which I call it n. So possibly you recognize this n quantity is the one if you solve the hyperbolic, the scalar field, let's say, in a Kerr space-time, the Klein-Gordon equation will give you this constant, will have you this constant, everything will depend on this n. Here is for space for d equal 3, space dimension, and this is the mass of the scalar, and this is the cosmological horizon. Now, what is interesting here, and I just show you the plot, is that for a particular value of this n, for 1/2, this is conformally coupled scalar. So here they have the plot of the C6, this is C6, in terms of n squared. For this particular value, they normalize it with n/2, and this is because the n/2 value gives you the flat space result, because you have space like a surface, and for constant time, and this is, you expect that this is a conformal flat space, so you expect that when you have a conformally coupled action, you will get the same result for the entanglement entropy. So then the next, some years later, these people here, they have generalized exactly the computation that Magda Sena Pimentel did, and they computed the entanglement entropy in the alpha vacuum, and they found that the entanglement entropy in any other vacuum is larger than the entanglement entropy in the Bunch Davis. So the minimal value for the entanglement entropy, it happens to be in the Euclidean vacuum. So let me just now show you how an attempt to compute the entanglement entropy using holography. So I just start by just pointing out the generic setup, and the next slide I will focus on the particular computation. So here I'm taking, let's say, a generic metric. So this is the radial direction. This is my space, and this is my time. My metric depends only on the time and the holographic direction. Now I will choose a rectangular strip, and I want to compute the extremal surface of this rectangular strip, and this by this proposal will give me the entanglement entropy, the degrees of freedom here and the degrees of freedom outside. So what I do here is I will take a strip that looks like that. That's my boundary, my de Sitter boundary. This is one direction, and this is the length of the strip. And this is a parameterization, this is how I parameterize this surface for this metric. So here, sigma j are the parameters of my surface, and I'm taking them equal to the space directions, and z and time, the holographic direction and the time, are dependent on x1. So this is basically, this tells me about, this gives me the shape of the surface, the sigma dependence. So here is my boundary conditions. Basically here it tells me that I am in a strip, but I have a strip. This one tells me that I will integrate over all the other directions, and these are my boundary conditions. Basically this tells me that this surface will come up to the boundary here and here. Okay. Now here I see that this surface I expect to be symmetric, and I see that it takes a minimum value at the bulk, which I will name Z0. So now the action takes this form. Now you see the alpha is just a volume, integrand, and here in the t is the whole, is the derivatives of my space. Okay. By solving, in principle, by taking any time-dependent background that has these properties here, that has this metric, I can solve the system numerically, and I can find what is the entanglement of this space, of this strip. So it is a space-like surface, extremal surface computation. Now I will apply this thing directly to what I showed you before. I will take that de Sitter with the de Sitter slicing. This is now my metric, and this is my planar, this is my conformal coordinates I will consider. Now x0 is my time, and if I write it if I would just plug everything inside, I will get the formulas I told you before. This and this from these actions. Now, in principle, you can do the computation as I said numerically, but I will not show you numerical results in this section. I will show you in the next one with the Wilson loops. But I want to demonstrate you how you can do it analytically when you have an ADS3 space with a de Sitter 2 bundle. Okay, so in this case, everything reduces to something very simple. Here, I will have a geodesic computation. Here you see my previous answers will be only dependent on sigma. So my extremal surface become an extremal geodesic. And if I do the computation, I will get something that is very nice. Here I will say I will get that all the bulk data or that the minimum surface has related to the boundary through this conformal factor here. So this is directly a hint that maybe we'll get something that is equal, the element will be equal with the flat space-time. Now x0 sigma and z sigma can be found analytically. They're not so important to show you now. Here z0 is just this point of the minimal surface in the bulk, and you see that how it is related with the length of the strip at the boundary. Okay. So I will. So if I compute now, if I minimize the action, I will find something that looks like that. So here, this is a cutoff on the sigma on x1, and I will find that the entanglement entropy is that it has the usual logarithmic behavior, and here is my UV cutoff. R now is the radius of the de Sitter space. L is the length of the strip. So then it is a demonstration how you can compute analytically the entanglement entropy in the DS3, DS2 with the DS2 boundary. Now I can go a step further, and I can compute the 2-point function just for consistency sake. I know what is a 2-point function because I have a conformal theory, but I want to compute it using the geodesic approximation. No, this is a usual way to compute 2-point functions when you cannot apply the bulk-to-boundary formalism. For example, when the people have time-dependent solutions like the ADS Vaidya, where a black hole is formed, and they want to compute how fast it thermalizes, they have to compute some 2-point functions. Of course, they cannot do it with generalizing the bulk-to-boundary formalism, and they can apply this geodesic approximation I will show you now to compute the 2-point functions. So we do something similar here. So I will take, I know that the equal time propagator here is given by a path, by the path integral over all the particle paths that end on x and x prime. Now, if I take a saddle point approximation, this path integral here localizes the sum over the geodesics between the 2 points x and x prime. So then I can prove that this 2-point function in large n is given by this formula. So here basically what is important is that the mass of the field is equal to the conformal dimension delta, and this edge here is the geodesic. So by knowing the geodesic, I know the 2-point function. Now, because I'm in conformal field theory, this should turn out to be equal to the inverse of the geodesic distance. Okay, so I will apply this logarithm here. This basically is the logarithm is my geodesic action. So here is the mass of the particle, the conformal dimension. This is my geodesic length. If I will put it in the formula I showed you before, I will find that this equal time 2-point function between these 2 endpoints is equal to the geodesic distance of this point. So this is a demonstration how it can work in a time-dependent backgrounds. So here the geodesic distance is equal to this because it's equal time. So I will have here the length, and here this is x0 squared. This is the value at the boundary, the time value at the boundary, and this is the length of the coil of the string. Okay, so this is the way to compute the 2-point functions using the entanglement entropy. Now let me go maybe to some more analytic work. I will show you some way to compute the Wilson loops in the simpler space-times. So the Wilson loop, we know that there is a trace in the group representation of the path order exponential of the gates, of the integral of the gate fields along the loop C. Now the group representation I will choose, it will be the fundamental one. So I will have to do with strings in the gravity side, and my gates and the shape of the loop, it will be orthogonal. It will be orthogonal, a rectangular loop on the boundary. So if I do the Wilson loop operator of the orthogonal loop in the large time limit, is related to the static potential, to the energy of the Hermite quark bound state. The first correction is the static potential, the energy. So basically that's the picture you have at the boundary. So you put two quarks in the flat Minkowski space-time, and these two quarks, they make this Wilson loop. This is my time direction. They are infinitely heavy, so they don't move, and this is the distance between them. So that's why you have a rectangular Wilson loop. So using the ADS-CFT dictionary, we know that this the expectation value in the large n limit is given just by the minimum surface that ends on the boundary of this particular Wilson loop. And this is everything can be, let's say, factorized in terms of how did the surface go along the holographic direction. Okay. So for this one, I have some complications compared to Minkowski space. I will choose the coordinates that are planar, and I will put two heavy quarks on my de Sitter boundary. And I want to compute what is their energy. So if I do that, I will put two quarks here on these geodesics, they will start diverging from each other. Now, I don't want this divergence for computational, basically, reasons, because I will get partial differential equations to solve the problem. So what I will do is, instead of having divergent quarks, I will give an energy to quarks. So I will give a speed to each of quarks just to counterbalance the expansion of the space. So I will have the invariant distance of the quarks at the boundary to be L squared, and the velocity that I have to give to each quark pointing to each other. So a quark here will point in this way, a quark here will point in the other way. We have this value. Now L is the distance between the quarks, and H is the cosmological horizon. Now if I do this, I will achieve a translation symmetry for the Walser, which means I can solve the system using ordinary differential equations.
I have a question. In your previous example, this answer for x0 is dependent on sigma.
Yes.
But normally we take a time slice and compute the entropy. But so why?
So this is a space-like surface because it's time dependence. So when it's not time dependence, you can set it to 0. But when you have a time dependent background, you have to take a space-like surface, and so that's why they have found in this area. And then the space-like surface introduces the entanglement entropy correct. So the difference is that one background, if you have time dependence, you have to take space-like surface, but involves the time dependence.
So can't you do this similar to your core functions?
In principle, you can do it, but I don't know. Yeah, I don't know if it will be something like Wilson loop. In principle, you can parameterize the surface like that. Actually, we have found these kind of solutions, but
the interpretation.
The interpretation is not very clear. Okay. Now I will just show you. Now this is the parameterization now of my Walser. So here is this is tau and sigma are the Walser parameters, and these are my space-time. You see here that I have the time dependence on the x1. This is basically the velocity that I give to the quark, and here is how the surface parameterized in the boundary. Now the boundary I have sigma is equal to lambda L. Now this is a consistent answer if you put it in the full equations of motion. And here the energy is given by this formula. Notice the energy of the quark. Notice that there is no time dependence, although you are in time dependent background. And if you compute this is I integrate from 0 to a sigma 0 is just the turning point of my surface, and I know it's symmetric, so I have to multiply by 2. And by doing so the z of sigma here, to find the energy, we have to compute what is z of sigma, and z of sigma is given by this quite complicated differential equation. Now the nice point here it is complicated, but it is an ODE, so it can be solved in principle. Okay, here you don't have time dependence. Of course, before I show you the solutions, let me tell you some things about how to regularize the energy of the quarks. So the Wilson loop here is infinite, and there are two ways that we can use to regularize the action. One is the Legendre transform, and one is the subtraction of the thermal mass of the quarks. So here the Legendre transform can be justified because in the transverse to space-time directions, the minimum surface has Neumann boundary conditions. So the Nabucco action is appropriate for the Dirichlet boundary conditions, but when you have a Neumann boundary conditions, then you have to take the Legendre transform. So the Legendre transform is just we take the Nabucco action and we add a boundary term that looks like that. So here is the conjugate momentum along the z direction, the holographic direction. And here I have 2 points, S1 and S2 are just the endpoints of the string at the boundary. And T is the time direction. Now if I take now the variation of this action, it will end up to be a function of the conjugate momentum. So this is how you use the Legendre transform to get rid of this element of the UV divergences. Now this scheme has a disadvantage, and the disadvantage is that it sees only the UV region. So if you have a heat bath, let's say if you have a black hole in ABS CFT, then it fails to capture the infrared contributions. So that's why the people usually choose to subtract the infinite thermal mass of the single quark. So this is basically, you find the energy of a single string instead of connected string, you find the energy of the single string hanging down to the bulk. And here is what you have to subtract. So this is a function, but it's not important for the moment. But you see here that this is, for example, my boundary. This contribution of this energy is equal with this one, but here you pick up a contribution from the infrared region, from the bulk of the space. And this contribution from the infrared region usually has the thermal properties. So, nevertheless, in our case, it's quite difficult to find single string solutions with the boundary conditions we consider. So it's more challenging to use this scheme. Okay, so let me now show you some pictures. These are the numerical results of the string solutions. So here, let's forget about these two at the moment. You see here, here is my boundary for z, let's say equal 4. And this is my bulk, and this is how my minimum surface looks. So I'm taking a particular time slice. I'm slicing the surface along the time. This time translation invariant. So I'm just taking a particular frozen time, and this looks like that. So you see it's symmetric with this axis. Now, if I start increasing a little bit the length between the string and points of the quarks here, I will start seeing some deformation of the string. So my string around its turning point seems to be starting pulling away, to be pulled away. But this, you see, this is not a regular behavior, because if I go for these two small ones, smaller distance ones, I will get a bigger deformations. So somehow there is some kind of phase transition on the way that these solutions work. And this can be explained more clearly if I look, for example, at this plot. So here are my quarks, are the boundary of my de Sitter space, and this is my bulk here, and this is the distance, right? This is the distance between the quarks. Now here, if I consider this the distance, let's say L, this one, I see that I have two minima surfaces with the same boundary condition. So one looks like that, and the one it has a deformed endpoint. Now this is an effect. This is a clear effect of the cosmological horizon. In this case, of the string vortex. And if you want to see what happens, for example, in a summarized plot, you see here, I plot the length of the string in terms of the endpoint, which is here for the minimal surface, and for every distance between the quarks, I have two different minimal surfaces. So this happens. The same thing happens in the gravity side when you have a thermal field theory in the flat space-time. If I had an ADS black hole in this theory, let's say if I have an n equal 4 supersymmetric mist in finite temperature, I will have the same plot but with a different mechanism. So there I will have double solutions because the black hole will pull the string down. But here I have double solutions because this string here with the same boundary values, because this thing here is defined by the cosmological horizon. So there are similarities with the thermal cases. Now, if I compute the energy, of my bound state, yeah, I will expect to be a function of the length, 1 over length, at least close to 0 temperature, and then I will expect to be some kind of combination of the cosmological horizon and the length. This is due to dimensional analysis. So of course you can do analytic work here in some kind of limits, but I want to show you the plot of the energy of my bound state with the length of the bound state, and this, you see, has a maximum length beyond which the state does not exist. So here, if you see, is like 0.92, let's say, of I have normalized everything with the cosmological horizon here, and this beyond this point, this turns back, and I have this double solutions. So for its distance, interquark distance, I have two energies. Now it turns out that the one that is energetically favorable is the one that is, of course, below in this plot here, this segment. And this is also the one that is stable. So this is exactly the picture you get when you have finite temperature field theories on the flat space-time. Okay. So this is also backed up with some similar computations by these people. For example, here they have taken the thermal fluctuations, the Brownian motion of particular strings due to the cosmological horizon, and they have computed the Lagrangian coefficients in the Brownian motion. And indeed, they have found that, for example, in the Sitter field theories, the thermal effects are present. So similar, like having a flat space computation of some finite temperature field theory. Okay, now I will just show you one more plot without going to the computational details here. Is a bit more complicated, but here I will add one more parameter in the system, and I will make some spinning mesons. So I just rewrite my metric in this form so to have obvious the rotational invariance to make my life easier. Here I will go to the equator of the space, and I will compute. This is my rotation here. I put here f sigma is a function that has to be found by the equation of motion, and this is my answer. So basically, I have two rotating strings along the equator of the sphere and the Sitter space, and then I want to compute what is their energy compared to the angular momentum. Now I will, if I compare the static ones are this one, and the spinning are the red ones. You see that already the spinning strings have bigger deformations due to the cosmological horizon. The red are the spinning, the static, that they don't move, are the spectrum. And if I compute the energy versus the angular momentum, I will find these characteristics plots that we have in the finite temperature field theories. So my energy squared and the angular momentum will have a particular point, and then it will turn back. So there is a maximum angular momentum for a constant interquark distance that I can have any spin, that the state can exist. Okay, so this is also a characteristic of the finite temperature field theories in the flat space-time. So let me summarize so far what I have done, and maybe I will spend very few minutes also to show you the boundary formalism. So far, what we have done is that we have computed the energy, for example, of the energy between a quark and antiquark, the static potential of the heavy meson, or the energy of the spinning mesons. And in all the cases we have found that qualitatively, not quantitatively, qualitatively they produce results similar as to having field theories on the flat space-time with finite temperature. Okay, my de Sitter field theory on the curved space-time gives similar qualitative results to the field theory in the Minkowski, let's say, space with finite temperature. Now, in the very few minutes, in the last minutes I have, I will just show you a little bit of computation of the 2-point functions. Now, just let me tell you in advance that that we know the result, right? We have a conformal field theory. So a conformal field theory, when you compute a 2-point function, you expect that you will get it proportional to the geodesic distance. But we do that just for completeness to show you how the bulk-boundary formalism can be applied in time-dependent theories. So maybe I will not have to go through this slide, but just the conformal transformation will give you a factor of lambda in front of the metric, and then we know that the scalar operator O of the conformal dimension delta will be transformed like that. So the 2-point function will be a function of the geodesic distance to the power of the conformal dimension. Okay, now it will be about the masses of the scalar field. I will just have it here. The question I got before. So that's my holographic setup. Here you go. I just start with a completely generic metric, and I just say that around the boundary I will have my factor here that tells me the asymptotic of how my metric approaches the boundary, and this is my space-time metric. Okay, so this is my metric, and around the boundary, this parameterizes how it goes to the boundary, and this is my actual space-time metric. And I know that if I want to compute a 2-point function, I will just have to compute the field. I have to compute how the scalar field f of mass m is behaving in my ADS background. Okay, so this is my scalar field equation with a massive scalar here. This is, I can write it like that. This is my my equation of motion. This is my boundary term. This is the usual equation of the Klein-Gordon-Vector operator, and this is how my boundary term looks. This is a normal vector at the boundary. Okay, if I don't want to do it brute force, I have to define the asymptotic behaviors of the scalar field. So I will define that my scalar field goes to the boundary with an asymptotic behavior of f, which I have to determine later. And then I have to use the bulk-to-boundary propagator k to express the field. So my field will be expressed by the metric at the boundary, the square root of the metric. This is the determinant of the boundary metric. This is my bulk-to-boundary propagator given by this formula, and this is my field on the boundary. Okay, this is the usual bulk-to-boundary propagator. Okay, I just show you two final relations before I end up, because I think I'm already getting over time. Now I can define my 2-point function here can be expressed in terms, if you do the bulk-to-boundary formula using generic metric I showed you before, this can be expressed in terms of the bulk-to-boundary propagator, the asymptotics of my metric, and my scalar field asymptotics. So by knowing these three things, I know the 2-point function of my field theory at the boundary. So now I say I know this, I know my metric, and I have to compute how my field goes at the boundary and what is the bulk-to-boundary propagator. And this can be computed. The bulk-to-boundary propagator, I will compute first the bulk-to-boundary propagator, and the bulk-to-boundary propagator can be computed, can be related to the Green function by just writing by just using the expression for the scalar field and using some divergence theorems. I can find that the bulk-to-boundary formalism is related to the Green function, which is here 2 bulk points, 2 points at the bulk. This is my my field dependence close to the boundary, and this is my metric dependence close to the boundary. So this is, now I'm going a bit fast, but I just want to show you, this is the relation, the final relation. This relates how the boundary propagator related to the green functions. So more or less I have all the formalism to apply and find 2-point functions in conformal field theories. Let me just, before I finish, I will just flash this slide and how we can apply this. Here I'm taking my ADS metric with the de Sitter slicing. I can compute the asymptotics of the fields close to the boundary, and these are given by this exponential behavior. This is my conformal dimension delta here, and I know that because I am in the ADS space and the green function is scalar, I know the form of the de Sitter of the green function. Now, if I take everything using the formulas I showed you before, I can find indeed that the 2-point function in the de Sitter space-time goes as the geodesic distance between two endpoints. Okay, let me finish here. So, what we have seen today is that particular observers like Wilson, Loops, moving Tortonia, entanglement entropy have been computed on curved space-time theories using the holography. So most of them, they hint the presence of the thermal bath, and we can just reproduce by entanglement entropy also the scalar 2-point function using the geodesic approximation. The de Sitter heat bath seems to be qualitatively equivalent to the heat bath of the field theories with black hole dual in flat space-time. Of course, so all the results qualitatively they look similar, quantitatively they have different expansions. We have also reviewed a little bit again the general back-to-boundary formalism for 2-point functions and scalar operators, and we have found that this formalism can be successfully applied to the de Sitter boundaries, where we have computed the 2-point function and we verified that we get what we expect. And this is a question for the future. Here there is a potential string theory dual that is equivalent to some N=4 super-conformal Yang-Mills theory that has been constructed relevantly recently. So there is so the argument is that possibly our gravity dual solutions have dual field theories that they have been constructed in this paper, but this has to be remain to be proved rigorously. So that's all.
Any question?
So in this Mason case, can you find some kind of color symmetry restoration when temperature is high enough by this construction horizon? Usually we expect that the temperature high enough will restore the color symmetry.
No, but here I don't have any flavor diffusion gradient, so I just have two mesons. So I just have a meson in the Glonic bath.
But you have this open string, right?
I have the connected string that goes to the boundary. So this the only thing that you can find from the meson, from the Wilson-Loop computation, when you are in the Glonic bath, you can find just a phase transition between the meson state and between two single quarks, because I don't have any more diffusion flavor.
So otherwise you need to put some flavor string.
Yes. Okay. If I have a flavor, so recently there are people trying to put flavor brains, and I think they succeeded. So in this case, I will expect that I will find this. It's possible to find in this case, but we haven't seen it.
So just was the integral structure, so the ADS structure is the same. So you are not working in with the slice, right? So by taking a slice, what happened to the integral structure of the slice?
Okay, so I would expect that there is still integral. Because you still have a conformal field theory, possibly is exactly conformal. At least the strings that are in the bulk, you can map them one-to-one to the strings on ADS with the Minkowski boundary. The strings in the bulk, there is a conformal transformation to map every string in the bulk to every string in the bulk of Minkowski space. But a rigorous proof, I don't know. I don't know if
Exactly, in the Fujita slice, time translation is broken. So how to define the code of charges or
How to define what?
time translation is broken, right?
Define what?
So then how do you define the code of charges or conservation rule?
Well, you can go to static coordinates and then you can restore it. You have a timeline. There you have a timeline vector. With static coordinates you can restore it.
Properties like data function or SF2C inheritance or integrability have to be very similar to the any possible. And infrared property are expected to be different. Just this field has a vacuum which is conformal invariant vacuum, which is very similar to the Minkowski field. So for the unit property, then you don't see the information from the curvature on the horizon. So we expect those properties will be the same. But to prove it, then we have to use a rigorous machinery of quantum field theory in curved space-time, like E properties. So that takes some time. Okay, if no more questions, then let's
Okay, thank you.
this point.
Probably actually, so leaving
Yeah, okay. Yeah, for the match. The funny thing is that when it goes to the progressive, they have the share. All the stuff. We're waiting for it. Yeah, they put in bugs. It's like right. It's either there or here. It's all the stuff. So how do they do that? It's not legit. Real problem. No, they have they have classes.
Nobody will
What is
所以硕士去做，教他去大概学生最好幸好听说那里有几个有几个有你的活动没有直接去通过
No, no, in Taipei they just how do you do it? So we spent half an hour. So it was very lengthy discussion and talk.
Nobody can do anything.
Yeah.
We have to do something before you do.
We like to, yeah. No, I mean, yeah, but I think if, for example,
Who asked you about
the guy who was discussing with him, the guy who was discussing with him, they would talk. The younger, right?
Yeah. What?
The young.
It's not young. Nobody is young.
No, but the one that is doing the amplitude, I think. This is the one that is close to you.
Oh.
昨天我跟他聊，他跟我讲说他蛮喜欢的是那个他最近跟我聊一些东西，所以什么某一些东西的那个数学结构，他看到某边，他跟我讲说，如果看到一堆某边的就很爽。
Yeah, people started eating, so we can try to do it tomorrow. You ever found? No, I still did the same. Maybe they left already.
I think you'll see it. 其实就是直接斜的这样子，就直接这样斜的长，然后再剪到这边。这个有看过吗？这就是它。
前面一点拖啊，多这么久才讲。
不可能刚好一样，因为你的 F 中它有很多交换的东西在里面。那 Cofactor 它里面交换它有刚好反正你可以确定你直接斜着层，然后再剪掉两边就这样。这个跟小的角度它是斜的。
对要少。
对吧？4成这就是因为你因为少层。是因为它就是只有这种这种。
都会。
那我们小它就是没好，但是它就是把它在里面。因为我们不是都会写2倍的8号或者8号。
2倍啊，那个就是有包含，
对，就是那里面的组合，有个数写在外面。那我可能他习惯把那个个数写在8号里，就那其实他。可以说，你觉得是他们做实事的事情，他做研究的习惯，他只看结构，他不看内容。但是其实跟他讨论的时候，他结构是在做，可能那个系数不够。然后讨论，最后要调。 了3张那个方面的被输了方面的，然后发现中间有个地方不是减号就是加号，但是我检查了1个月，我实在不知道为什么我改错，所以我从头算一遍。那个地方我不知道1个月，我不知道什么意思，超烦啊！用电脑也看不到，你要看。第二个话是居放，这个是上机对，那个变数当名的2晚。把这 AT Pro 带进来。这个那个跟它消掉一次，这就是一次。对，G 帮给它，就 G 这个把这个G 放积分这个提出来，所以这个时候原本因为做了大名 test 就是把它做成小 YG 记到 Y，YG 这个 A 也变成S 啊，然后记到 Y 之后呢，再把 Y 积分到。YG 再进去不会好看，因为它这个就是这个积分的关系，这个 Z 那如果你要再自己出，它就会变成大名的照片。哦，我知道为什么学到。 就是我也有压力，看起来像是动不动就累死。
还好吧，这才正常。
负担重啊，一直迷啊，一直迷啊。现在也觉得，因为有时候老视频跟 active 不想要知道什么东西，然后他自己会算，他说什么我回去算的这边你又不算。
然后反应节目咬我，然后你问他什么，他不知道，这样你才会做这东西。就是我觉得已经有这两个东西，样子看起来很像是他的结果，就是其实我还有一个机会是，只是已经这种是我需要帮助他们把这个地址，然后第一个
全味都很硬气。
所以没有它的形式的话，就会一点一点打在下面。这边都有自己的选择。对这个地区可以，所以我现在就最后就是这个。然后这个营业税里面是做自己的都要分析。第一个地方是 AT 这地在 PPT 里面有一个地在看，就是前面两个地。这个东西直接搞就是处理。第一项是自己带你的量，第二项，然后你的地的一阶就定，统计下地点也可以。下面这个缝不确定。还是说这里应该说这个是一个名字。超不介意的是。
现在这个太久了，对，就算准字，我之前用的那个是准字的。
放在上面，然后把它装进。
多少人签吗？
除非你今天一定要换。
这还蛮容易的。
真的吗？
你用一种要注意它。
我之前练也是这样，然后我之前有另外敷衍练很久。
是近况7年的吗？
也就是说，我就要把我应该算出来。对啊，我以前就所以我大概知道为什么会这样。可是我是那个镜片的那个钩啊，已经有点磨损了。
我换过镜片，但是镜头用的，因为里面那个螺丝这个地方应该是不是这样。 直接写，直接在写。
这里面这里是完全这个外层，然后前面打孔，因为它不会知道。
收到一封信，我不知道他是寄给一堆人，还是问我有没有在做批评。对，他说做这样啊，那看起来像是要他有问题。对啊，他要那个他在 tutor。不能交啊，不能交，听的这件事情很有趣，因为像系上有时候会就是他们会有人跑进系上，然后或者演不到，然后他们就会那个去交。这里面就是我们这里就搞romantic，我搞然后我是搞我之前看那个。对，没有，因为那时候没有决定。我想一下，讲过，因为我实验课，然后本身就已经成为。直接到时候去那边，然后就开始准备弄历史。我怎么讲？我之前有看到他们有教你怎么弄历史。不是，就是你。 能就是去学校，然后呢找，然后不知道怎么样弄到一堆网站，对，然后他就直接email给我。可能他们觉得大学生那本来就没有什么硕士生。要不然他女儿是大学生。我真的有一个大学生，那个感觉，你要说什么非自己生出小孩，觉得他挺不好，希望老师成长。有这种事。
一个点一个点。 需要负责任。然后第一光就要
交通那个。就出了几个最大的乌龟群记得是其实是穿这个衣服，记得是穿着衣服，男生的衣没有那么，男生不是不对，就对，没有那么华丽，是有点武士风。因为男生浴衣都很素。因为现在大家都分长袖，像东北那边是男生对，去的时候，因为鬼节，所以一定要当菜的这个一下，就菜的就先菜。我们那时候感觉那时候我记得感觉就有点小浪费，就浪费时间，浪费时间。是，就是要这个菜就真菜，对。我那我也还是没有查。对，我听说去的这里可能学我转正。如果真正的菜的媒体还是不去想，所以才还有很多人应该是我们那个键盘鸟去。你去过鸟居都在福建吗？福建到应该说这样 Google 的比例时代。跟团的话就不用问了，就打电话。你们推荐去古瑞山吗？古瑞山我没去过。最近应该都是3级，就是大概要克服配置都是3级。可能还是不要在外面待太久。
这是不是下一个中暑？他说是还要去大阪日本吃，那就很光。就在暑假期间去深圳去，
还是有3级比较好的，不是应该10月多2月3号，然后顺带去看红叶。
没有，刚刚有人不要去不行，每个。
也有黄牛找的。但是要它有好几种，而且你还可以比一下，因为它每个黄色都选的。
其实你只要打大概，就是在想要怎么搞。不要打，不要打。
如果他是说，对，但是就变成是有一个地方不想打一下，就是走路时间。
明明就4张纸可以算出来东西，算了4页。是的，这样。到他那怎么写的？然后。一开始就是第一次写的时候，
有2节都是上学校，3个点都在。
3个的话就是你要旁边就在旁边。
这个。
你看这种玩RPG有机会说不定变。
还是排这个风格就是有越写它。而且所有支线都要这样可以删减。
所以他玩仙剑奇侠传一个晚上过了，可以4万主线，然后直走主线，就是找那个特殊的道具都可以打 BOSS 打好起来，
像这种，像芭比，我也提到过，我是因为不知道怎么不行的。
有些没写部分，黑板都是黑板之后。
because there's no like people like not and there are no circles that we were localized. And then like it's both I mean you deal with free pay or
细胞个数检测。
我这是一个军。
应该是听到明天的。
ラジオトピア
Please look.
Yeah, I'll do it.
We'll begin our first talk in the afternoon. The first talk will be given by Taro Yoshida from Chicago University.
like to thank organizers for giving me the opportunity to give a talk in this wonderful workshop. Today, I'd like to talk about recent progress towards establishing variety CYB correspondence. CYB here is the relation of classical analog equation. This correspondence says that the relation between solutions of the type series gravity and classical R matrices satisfying classical analog equation. So this talk is based on mainly two papers. The first paper is for superposition construction in number-study form AS-5 string action. This is a collaboration with one of my students, Yono, sitting there. And the second one is a paper on relations between generalized supergravity and Moabian classical R matrices. This is a collaboration with Domenico Roland and Sandra Park with the University of Bern. Another student which so now I realize that this title is not so appropriate. So maybe this title is more appropriate, I think. So the title is Generalized Gravity CYB Correspondence. So I hope that at the end of my talk, you can realize the meaning of this title. Okay, so anyway, let me begin with the introduction. So here, we are interested in the typical examples of initiative correspondence. This initiative correspondence is a conjectural equivalence between type 2 group theories defined on ADS-5 platform and for the major manifold post-Mariamine theories as the Ryan gradient. So this is progress on this duality is the discovery of the integral structure behind this correspondence. So why integrability is so interesting? So integrability is so powerful. So the integral structure provides us a non-perturbative method to analyze the conjectural relations. So one can check the conjectural relations if you want to find coupling by utilizing the integrability techniques. So for example, we can compute exactly our dimensions of complete operators for scattering amplitude on the ACL chart. So integrability is very powerful, and indeed there are many directions of studies based on the integrability. Here, among them, we are concerned with the classical integral structures on the string theory side here. So I will use the term classical integrabilities in the sense of kinematical integrability. This kinematical integrability says the existence of Young's pair. So this kinematical integrability is defined from the usual complete integrabilities in the sense of theory, which says that explicit constructions of action and variables. But here, we will concentrate on kinematical integrabilities. So much precisely speaking, we cannot show the complete integrabilities for the ADS-5 superfields due to the content of non-local term in the partial structures. So,
when you say integrability of the string, is it integrability or as a field theory?
Two-dimensional field theory. Yes. So anyway, so we will consider the complex one-dimensional theory, that is the string versus theory. So then we cannot apply the Lewis theorem. So that's why the notions of integrability is subtle. So we should be careful for the time. Okay, so anyway, let's recall the classical integrabilities of the ADS-5 superstring here. The process structure of the ADS-5 background is closely related to the integral structure. So you know that the ADS-5 background can be represented by this symmetric concept. This is the symmetric concept, so this concept enjoys the grading properties. These grading properties ensure the classical integrabilities of non-Yoshima model whose time space-time is given by this concept. So then, this is just a botanic part. So then, we want to provide this symmetric concept by including space-time values. So then, this symmetric concept is replaced by this superconcept. So then this superconcept enjoys the default grading instead of these grading properties. So this grading properties ensure the classical integrabilities of this super system. This point was initiated by Penapolchinsky and Roland in 2003, and this part becomes the starting point of our other arguments. So anyway, we know the classical integrability of the ADS5S5 superstring. So as the next issue, we want to consider integral deformations of ADS5S5 superstring. So anyway, we can perform integral deformations as exactly solvable models. So we know that the string theory is 1 plus 1 dimensional integral system. So we can apply integral deformation techniques. Then the target space times are deformed. So we can get the deformed ADS5S5 geometries. So then one may expect those deformed geometries may be solutions of type series problem. So this is just expectations at this moment. So on the other hand, we know some integrability techniques in the context of exactly solvable models in mathematics. For example, integral exists, such as Greenfield exists or Schilling exists, or many integral exists are known. So we know some solution generation techniques in the context of type series progression, like TST transformations. So we can expect the correspondence between these techniques. So one may consider various kinds of integral deformations by performing integrability techniques for the ADS5S5 superstring. So there will be many associated solutions of type series superproperties. So this is just our observations at this moment. So our motivation is classifications of supergravity solutions from the viewpoint of integral deformations. Okay, so along this line, we have letters for the systematic way to study integral deformations. Of course, we can consider integral deformations case by case, but such approach is quite annoying. So we want to use a systematic way to study integral deformations. So now we know such as convenient systematic ways to study integral deformations. That is called Yang-Baxter deformations, which was invented by Primitive in 2002, and the formed sigma model was integrable. Integrability was shown in 2008 by constructing the Raspberry stage 3. Okay, so here I'd like to introduce Yang-Baxter deformations by taking a simple example, three-dimensional G-principal parallel model given by these classical actions. So this action contains the factor J mu. J mu is the usual left invariant one form. So this is the original action. So then we can perform Yang-Baxter deformation by inserting these factors here. So this deformation scheme is very simple. Just inserting these factors here. And the integral deformations can be measured by this factor. This deformed sigma model action is called the Yang-Baxter sigma model. Okay, so let's explain the next here. Okay, so anyway, this factor is composed of eta and r. So when eta is a constant function, so when eta equals 0, the original model is introduced. So then what is r? So r is a linear operator. So the algebra gets to K. So this is a linear operator. This can be fixed by taking a classical R matrix in the tensorial notation that defines modified classical Yang-Baxter derivation. So anyway, integral deformation can be specified by taking a classical R matrix. So that's why we can study integral deformations systematically by following this deformation scheme. And here, I'd like to express advantage of these deformations. This deformation has a strong advantage. Given a classical R matrix, Laplace pair follows automatically. So there is no need to construct Laplace pairs in an intuitive manner, case by case. So if you have tried to construct Laplace pairs by starting from the equations of motion, so we can realize that such approach is quite difficult. So it's very difficult to construct Laplace pairs directly from the equations of motion. But now, by picking up a classical R matrix, then associated Laplace pairs follow automatically. So this is quite a strong advantage of this deformation scheme. Okay, so here I'd like to explain about the relation between linear R operators and classical R matrix in the tensorial notations. So there is a one-to-one correspondence between these quantities. So using these relations, we can get the operator to classical skew symmetry classical outcome in the tensor notation. So this relation is here. So by taking the trace on the second side here, then we can get the linear operator. So this relation is very simple. So anyway, even a classical R matrix in the tensor notation, by taking the trace on the second side, we can get linear operator. Okay, so then we can consider two sources of classical R matrices. The first one is the modified classical Yang-Baxter equation. The second one is the homogeneous classical Yang-Baxter equation. So this is the modified classical Yang-Baxter equation. So this is the right hand side here. This term is so that's why this Yang-Baxter equation is always modified. So and this modified classical Yang-Baxter equation was utilized in the original work by Glitch in 2002. So in the original paper was based on modified classical Yang-Baxter equations. But of course, for generalizations, we can consider classical Yang-Baxter equations. I mean, this term are boundaries. So then, okay, so probably, okay. So it's R in the term. This R. R. Oh, that's in the practice. This. Now, of course, you probably you're familiar with classical Yang-Baxter equations in tensor notation, but this Yang-Baxter equations is in terms of PR. So okay, so you can see these two are almost the same, but there is a big difference between two Yang-Baxter equations. So due to the presence of this deformation term, R equals 0 does not satisfy the modified classical Yang-Baxter equation. But in the homogeneous case, R equals 0 satisfies the Yang-Baxter equation. So R equals 0 is very important. When we can consider the partial deformations. So the R equals 0 solution enables us to consider partial deformations of the geometry. So anyway, that is the difference between the Yang-Baxter equation. Okay, so then let me show you the list of generalizations of Yang-Baxter deformations. So this list is basically composed of two classes. The first class is based on the modified classical Yang-Baxter equations, and the system belongs to the trigonometric class of integral systems, basically. So original work was done for principal chiral model by Glitch in 2002. So after that, Descartes and Isero generalized unique parts to symmetric coset case and ADS characterized patterning case. So, okay, so this result triggered some recent progresses on integral deformations of radius shifting correspondence. Okay, so anyway, this is the first class. And the second class is based on the homogeneous classical Yang-Baxter equations. So the closed system belongs to the rational class of integral system in this case. And similarly, we can consider Yang-Baxter deformations for these three cases. So we will consider Yang-Baxter deformations for these three cases. And now, precisely speaking, we can consider the third kind of deformations for Yang-Baxter deformations. But Yang-Baxter deformations is applicable only for principal chiral model. So we cannot apply Yang-Baxter deformations for ADS 5 case. But of course we can consider the Yang-Baxter deformations of ADS 6 background. But here we will concentrate on the ADS 5 cases. So we will consider these two deformations in the following.
What's the difference in properties between these two classes of
deformation? Difference?
So on the left side is particle harmony. Are they different in any physical properties? These two classes of models?
So actually, okay, so in several systems, these two theories are different. Well, first of all, the class of integral system is different. This case corresponds to the trigonometric class, I mean like C-like series. But this case corresponds to XXX also we developed system with different. And I think the supporting to this difference, the resulting symmetry algebra is also different. For example, sometimes affine algebra should correspond to this case, but in each case, we can find the probability diagrams or some rational algebra problem.
Second case is related, is some limit of the first case.
I think in some cases we can take limits from this one. But I think that not all of them can be derived from this case. Some cases can be derived as a limit of this case.
So the symmetry algebra can be part of the formation of the algebra.
Yeah. Actually, there's some cases
pure deformation.
Yeah, pure deformation corresponds to this case. Yeah. As I explained in this next slide.
What is the motivation of consider the deformation?
What is motivation? Okay, so of course, by performing deformations, so for example, you can remember the XXG models. So after performing deformations, the XXG models, so you can find out some interesting physical properties like phase transitions or non-visual phase structures. And so new physics is included after performing deformations. So that should be good. And of course, probably, okay, so someone suspects motivations of integral deformation, but after studying integral deformations carefully, so we may get fundamental progress on the string theory itself. So actually, I will explain later. So Arkady and Dinosaur does the fundamental progress by bigger integral deformations. That's important to study integral deformation. Okay, so anyway, let's consider some kinds of integral deformations of the ADS5 specified supersymmetry. This example here, so some defined names are described to describe the same integral deformations. Okay, so the first example is integral deformation is based on the modified Einstein equation. This deformation is called eta deformation, or standard tree deformation, or sometimes kappa deformation. So many words are utilized to describe these deformations. But I think the most popular one is eta deformation. So in the following, I will use this terminology, eta deformation, to describe this deformation. Probably you have heard another deformation called lambda deformation on chapter, probably. So lambda deformation is another deformation invented by Spectrus. And the lambda deformation is closely related to this eta deformation via personality qualities. So anyway, there is an intimate relation between lambda deformations and eta deformations. And the second one is based on the homogeneous Einstein equation. This is called Jordan deformation and standard tree deformation. So anyway, basically there are three deformations here. So then, by employing these three deformations, so one may expect relations between solutions of type series varieties and classical R matrices that explain modified classical Reynolds equation or homogeneous classical Reynolds equation. So relations may be for the gravity Shigari correspondence. So this is the title of my talk. And in other words, this is a conjecture that the moduli space of certain cluster of solutions of type series varieties would be able to be described by classical Reynolds equation. Okay, so then I'd like to show you the current status of two kinds of Reynolds deformations. I'd like to show you some recent progress on two integral deformations. Okay, so let's see. First, let's consider the eta deformations based on the modified classical Reynolds equation. So the result number and method constructed the Q-deformed classical actions by using the classical R matrix of Greenfield genotype. So that's why deformed action belongs to the Q-deformed ones. So this is called the standard deformation. So then perform coset constructions, but after that, Archimedes voltage prolog perform coset constructions for the bosonic element. So they determine the metric and the resonance form. And then last year, Archimedes voltage prolog succeeded in performing supercoset constructions. Interestingly, not interestingly, the resulting background does not satisfy the equation solution of the standard type 3 superclass. So this was shown in this paper. So after that, Archimedes for Loivan Zetrin shows that this resulting background is a solution of the general supergravity equations rather than the standard type 3 supergravity. So this modification means that the target space-time constraint is weak. So according to this modification, the world sheet constraint is also weak. So then world sheet theory is not invariant due to these modifications, but still invariant. So this is the main result of this paper. So anyway, for these data definitions, we need to generalize the supergravity equations from the standard one to the generalized one. And the world sheet theory is not very invariant, but still invariant. Okay, so all these data definitions mean other works have been done, including computations of minimal surfaces and co-content potentials. This is a progression with one of my students, Takashi Kaminama. And anyway, many works have been done for these data definitions. Okay, so then this is a Jordan definitions based on the homogeneous classical Yang equations. So in this case, we can find out a lot of classical R matrices satisfying the Yang equation. So first of all, so as I advertised in the previous slide, we can perform partial deformations for ADS5 to SPI. So we can deform only ADS5 or only ADS5. So this is an advantage of Jordan deformations. In the case of the modified classical Yang equations, we call zero does not satisfy the Yang equation, so partial deformations cannot be done. Okay, so then we have identified candidates or relative solutions for many classical R matrices in sheets of the works listed here. So at last, we have succeeded in superpositive constructions for some examples of classical R matrices. So in the following, I'd like to introduce the form classical actions and outline of superpositive constructions, and then I will show you some classical R matrices and the resulting factors associated with these classical R matrices. Okay, so this is the Lambda deformed ADS-465 superpositive actions. So this action is basically given by the necessary actions for the undeformed case. But here, this factor is inserted by following the Lambda deformation scheme. So when I call zero, the original necessary action is zero. And here, I will not explain about the details of these actions, but here, all these deformed actions, that error has been constructed. So the classical integrability is ensured in the sense of numerical integrability. And by explicitly constructing the Kappa transformations, the Kappa invariant has been shown for the deformed action. So anyway, this action is Kappa invariant. So we can see the consistency of string series at classical level. I mean, we can see the matching of the numbers of degrees of freedom on the worksheet. Okay, so here I'd like to note that the difference between the modified classical Yang equations and classical Yang equations is reflected in some coefficients or some quantities, such as log spares or Kappa transformations. So anyway, the difference is small. Also, I will not explain about the details of these points. D. Okay, so D is the linear combinations of the projection operators P1, P3. Okay, so SE2,2/4 has a G4 planing. So there are some projections onto the graded component.
and small d is the linear combinations of projection vectors. Capital P is okay, sorry, I can show you the definitions. Okay, so this is the definitions of small d, and this is the definitions of capital P. Capital P, the projection vectors defined on the inverse. This is what's metric, and this is integral tensors, and this is inverse. Okay, so anyway, here this action is written in terms of the group element. So the coordinate system has not been released here. So the explain of the classical action is quite abstract. So we want to introduce the coordinate system explicitly, fixing the representations of group elements. So this is a group element belonging to the C/4. And G is composed to a product GB times G. GB is an bosonic element of this supergroup. And GB is further decomposed into a product with its by part and its by part. And GF is a derivative element belonging to this supergroup. And GF is generated by certain charges QI. And theta i's are two minor wire spinors. So anyway, by using these parameterizations, we can expand the function. So more precisely, we have to take some parameterization for edges 5 and edge 5. So here, we will take parameterization given by these ones. So then, by performing the constructions for the bosonic element GB, we can get the metric for edges 5 plus 5 geometries in the concurrent coordinates. By this one is by the boundary coordinate, and this is standard plus biometric. Okay, so then let's see an outline of superpositive constructions. So we have introduced explicit coordinates by these parameterizations. So then we can rewrite these different actions into the canonical form given by this one. So here, so you can see the metric and NSN2 form and the equivalent derivative into the Ramon constraints and the Dirac here. So all of the components of type series supergravity are included in its canonical form. So in other words, by rewriting the prompt actions into this canonical form, we can resolve all of the components of type series supergravity. So the remaining task is to insert the explicit expressions of classical R matrix. Then by performing opposite transactions, we can revise the inductions into the canonical form. Then we can revise all the component fields of type series supergravity. So this is the scenario for the opposite constructions we will consider here. So first of all, I would like to introduce 3 examples for which the opposite constructions works perfectly. The first example is 3-parameter gamma deformations of S5. So this deformation is closely related to the classical deformations of A equal to Bayesian wave cells. So R matrix is given by this one. H1, H2, H3 are Cartan generators of SE4, and U1, U2, U3 are constant parameters. So anyway, by using this classical R matrix, by performing this opposite construction, we can get this pattern. And this pattern is nothing but the solutions constructed by Lee-Marus and Kurov in 2005. So opposite constructions works perfectly. So interestingly, 3-parameter cases are not supersymmetric, but even for non-supersymmetric pattern, opposite constructions works perfectly. So this is important point. And the second example is gravity works for supersymmetric gauge theories defined on non-quantitative space. So we will consider this R matrix. So it's P mu is defined by this one. And gamma mu is the basis of SE2, Actually, basically, P mu is a translation for dimensional microscopic space-time. So anyways, by using this classical arithmetic, you can get this background by performing superpositive construction. So, okay, this background is nothing but the solutions consulted by Hashimoto Izaki and Marzaro Soto in Cambridge in 1999. So, for this case, what is the non-commutative parameter? Non-commutative parameter is related here. So now theta 2, 3 is count on the non-commutative plane. I mean, x2 and x3 is non-commutative. And the non-commutativity is measured by theta 2, 3. So basically, this classical R matrix is closely related with non-commutative definitions. So this is a classical R matrix, but we can consider the quantum R matrix corresponding to this classical R matrix, and that is closely related with non-commutative definitions. Okay, so here I want to note that these solutions can be produced by taking a special limit of beta default values by. So in this sense, this geometry should be obtained as a special limit of beta default values by. And so I think the applications between the determinations and only a sample cases. So this is just an example. This is just one example. By taking a special limit of beta dimensions. Okay, so some example is showing us space-times. By using this classical R matrix, we can get this pattern. So this pattern is nothing but a solution constructed by Felsefar, Marzaro, and Felsefar in 2008 in the context of the holographic duals of quantum. This background is very simple, but the superpositive construction is somehow miraculous. So you can see that Dirac and Amogram sectors have not been involved here. But in the middle of computation, the various sectors become clearly meshes and quite complicated. So the translation of the conventional effects seems really miraculous. So anyway, we can get this simple background of the miraculous information, miraculous translations. Okay, so far we have discussed only abelian classical R matrices. These three examples are abelian classical R matrices. So what is an abelian classical R matrix? So classical R matrix is given by R equals LHP. Then A and B with each other. Then it is called abelian. If not, it's called no abelian. So this is the definition of abelian and no abelian classical R matrices. So here we have shown only 3 examples, but we have already checked many abelian examples, and all examples succeeded to produce the probability solutions perfectly. So there is no drawback. And so it seems likely that the superpositive construction works perfectly, at least for abelian classical R matrices, unless the complete solutions of type 3 supergravity. So this is the conclusions for abelian classical R matrices of this so So however, for non-abelian classical R matrices, it is not the case. We have provided some examples of non-abelian classical R matrices, but none of them have led to our complete solutions of type 3 supergravity. So we have to consider carefully non-abelian cases. So let me show you examples of non-abelian classical R matrix.
Yes. In all these abelian examples, these are related to T-geometry.
TST transformation.
TST transformation. And you don't know counterexamples. So all abelian backgrounds are such, or abelian R matrices, you can construct these backgrounds also just with T-geometry.
Yes, that may be possible according to my results. Actually, I will explain about it later. actually the final result is closely related to your questions. Okay, so here we would like to consider superparameter families of classical R matrices. These classical R matrices contain superparameters A1 and A2. So this is the superparameter families of classical R matrices. So anyway, by using this classical R matrix, we can get this pattern by performing superposition confined. So then let's take the derivative for F3. Then we can get this expression. This is non-zero. So DFC does not vanish. So the Bianchi identity of F3 is broken. So according to these broken Bianchi identities, we can immediately understand that the equations of motions of ET is not satisfied as well. So this background does not satisfy type 3 supergravity equations of motions. So here I have some comments. So the first one is a special case. So when we consider A1 equals 0, this term vanishes. So the Bianchi identity is satisfied. So all of the equations of motions are satisfied. So this is a special case. So classical R matrix becomes Arrhenian. The background becomes a complete solution of type 2 supergravity. This background is nothing but a solution constructed by Fedeli, Rangamani, and Ross in this paper. So this is a well-known case. So then let's consider the general case. A1 is non-zero and A2 is non-zero. The resulting background is not a solution of type 3 supergravities, but still satisfies the generalized type 3 supergravity equations. This is an important point. Then, by performing T derivatives for these solutions, we can get the solutions of the standard type 3 supergravity. So here, I like the quotation mark for the T derivatives. Because T derivatives are performed for the non-standard solutions, generalized solutions. So that's why the generalized shadow. So in this sense, I have the quotation marks for these T derivatives. Remarkably, this T-derived background can be rewritten into the undeformed AS5 file. So that's why this Navarian classical analysis may be understood as a T-derived transformation plus alpha. So this result is associated with arbitrary expressions. Okay, so in the following, I would like to explain the details of these results. So first of all, I'd like to show you the set of generalized equations of type 3 supergravities. So these are the equations of generalized type 3 supergravities constructed in this paper. So this is the equation for equations and equations for the system and equations for electrons and the identities are also modified. So what are the modified parts? So modified parts are specified by mean squares and mean squares and least squares. So these parts are modified. So this equation contains x and t and I and c vector fields as mean integers. So in this sense, these equations are generalized. So please don't confuse with generalized geometries by teaching. So I think that generalized equations are related to generalized geometries by teaching. Okay, so anyway, this equation contains new gradient x, y, and z. These are three vector fields. But now x is just a sum of I plus z. So now two of them are independent of each other. So then I and t satisfy the following relations. Assuming that factor I is chosen such that the derivative given by this one should vanish. Then the second equation here can be solved by these expressions. So in total, only I is independent after all. So when I equals 0, the usual type 3 supergravity is under this expression. progress on the principal strings. So here I'd like to explain about the relations between kappa symmetries and supergravity equations of motions. So probably you know that all the results, the on-shell conditions of standard type 3 supergravities express the kappa invariant principal string theories. This result was shown by Grisel et al. In 1985, and the inverse was conjectured as well in these papers. But this was just a conjecture, and the answer has not been provided for almost more than 30 years. But recently, Arkady and Linus developed solutions for this conjecture in a modified form. So this conjecture is not correct. So we have to move towards like this. So this is a new result shown by Arkady and Linus. So kappa invariant principal string theories rests to the generalized type 3 supergravity equation solutions rather than the standard type 3 supergravity. So this is the interesting impressive and fundamental results on the principal string theory itself. So actually this fundamental progress was triggered by studies of integral deformations. So in this sense, the studies of integral deformations was being used to make progress in the fundamental aspects of string theory itself. Okay, so anyway, this is very impressive results. So anyway, it is largely natural that the resulting background satisfies the generalized equations. So as far as the deformed action should be regarded as a principal string, the generalized equation should appear. But still, I have a question. Is the universal deformed action really the principal string? This so far, the answer for this question seems yes. But we still need to check the consistency with arbitrary classical R matrices, including higher order contributions of elements. Here we have considered the quadratic limerick actions, but we have not considered the higher order operations. So more precisely speaking, we have to check the higher order contributions of elements, and we have to check the identifications between the deformed actions and principal string actions. Okay, so anyway, let's return to the recent examples of non-linear classical R matrix. By taking I and C like this, we can show that the resulting background satisfies the generalized equations of motions. So this is the result of this statement. So then, by performing T dualities along x plus x minus y and phi, then we can get this background. So this background is relatively simple because this is just a metric and the alpha is not zero and the reaction is cancelled. So just a component is zero. So relatively simple. And this is the solutions of the standard type 3 supergravities rather than the generalized one. So anyway, by performing T dualities, we got the solutions of type 3 supergravities in the usual sense. So then, let's perform the following Fourier transformations. Then we can revise the trivialized background like this. So for this background, we can perform T dualities along x0, x3, pi1, pi2 immediately. So this metric, this background can be written as the undeformed areas by this pi. So this is not itself. It's surprising. So we are considering a non-linear classical R matrix, but resulting background must be written into the undefined areas like this pi. But here, this is not here that. So according to these Fourier transformations, half of areas pi corresponds to the trivialized background. So we have already fixed the transformation parameter eta. So when eta is positive, x tilde minus should be positive. So half of areas pi is half to the trivialized background. So anyway, we can see the equivalence of this locally. So I'm sure. So how can we interpret these results? Probably we can interpret this result as this is periodic bounded conditions across all points. Of course, for abelian cases, we can understand the results by following argument by Prolog or direction Prolog. So the formed background is equivalent to the undeformed background plus twisted periodic bounded conditions. So, but now we are considering the non-abelian classical R matrix. And we have passed through the generalized equations of motions. So probably we need some modifications plus alphas. But I'm not sure of the answer for this plus alphas. But anyway, we can get similar interpretations for these results. Probably these results should correspond to undoing the unitary systems. Okay, so we have studied just one example now, but we have already studied other examples of non-abelian classical R matrices. And all of them satisfy the general equations as assumed from the general argument of partiality. But other properties are different depending on the cases. So for some examples, integralized background cannot be mapped to the undeformed radius pi. For just as it seems that it's quite difficult to perform equalities. Because resulting metric is very complicated. So it seems quite difficult to perform equalities. So of course, we can give a proof for the impossibilities. But this for us, it seems quite difficult to perform equalities. Or to utilize resulting metric to the undeformed radius of the pi. So based on these observations, it would be significant to classify non-abelian classical R matrices. So for example, we want to answer these questions. What kinds of classical R matrices are mapped to the undeformed radius pi plus pi? I think that at least a certain class of non-abelian classical R matrices can be mapped to the radius pi plus pi, and we can give nice interpretations, at least mathematically, like the indexes or some very fine mathematical operations should correspond to the results. So along this line, probably this work is very useful. So they consider the scaling limit of the undeformed radius pi, and they derive some classical R matrices associated with background by taking some limits. Of course, all of the non-abelian classical R matrices satisfying homogeneous Yang-Russell equations cannot be obtained by taking scaling limit of eta to radius pi. But this strategy is quite systematic, so it will be useful to consider classifications of non-abelian classical R matrices. Okay, so let me summarize my thought. Here, I'd like to explain the recent progress towards establishing gravity-CYD correspondence. So firstly, for abelian classical R matrices, the correspondence works perfectly. So we succeeded in deriving the Schrödinger sample background, Weissel's background, and Schrödinger space-time particles by performing superpositive constructions explicitly. And non-abelian classical R matrices explanations of the generalized supergravities. So this is rather natural as far as the conduction is assumed to be the initial. The appearance of the generalized supergravity is intrinsic to the initial string itself, rather than the deformations, the Yang-Russell deformations. So the main message I want to stress in this talk is generalized supergravities underlie the gravity-CYD correspondence. So in this sense, the gravity-CYD correspondence should be based by the generalized gravity-CYD correspondence. This is the meaning to change the titles at the beginning. Okay, so I will stop here. Thank you so much.
Question? If you look at the property of the generalized gravity, for example, we have something generalized Fourier solution.
Actually, Okay, so we have constructed solutions of generalized gravity by performance purpose construction. But I think that there should be many solutions satisfying generalized equation, something like black holes or integral solution. But I don't know. But actually, according to this result, the avalanche theory, so which string theory should be given by generalized equations rather than the standard types of gravities. I think that it will be very difficult to construct such black hole solutions satisfying generalized gravity equations.
Generalized concept, how do you do it?
Actually, the Bayesian field I is unknown. So, well, okay, yeah. Actually, Bayesian derivatives depending element in capital I only. So, by using non-trivial I, we can get solutions of generalized gravity equations.
How about the super algebra? I is kind of some extension.
Okay, so here I have shown the equations of motions of the gravity of the component, but Kali and Linus fix the equations of motions for gravinos and gravinos in the papers. So by using the equations of gravinos and gravinos, we can get the P spinor equation. So we can consider the P spinor by solving the gravity equations and gravity equations.
So they have their definition.
Yeah,
for
this is just
supercharge
the
and everything.
state of work generalization of spiritual work.
And how about type 2B is like 10-dimensional string, but you have say 11-dimensional theory. So the only scale on the 10-dimension becomes the string length. In this generalization, you need to introduce another scale.
Another scale?
For the generalization.
Yeah, of course, we can consider similar generalization of type 2 supergravity. But the important thing is that there is a dilatons in type 2 supergravities and type 3 supergravities. But in the case of 11-dimensional supergravities, there is no dilaton. I think that there is no generalizations for 11-dimensional supergravity. I think this point was explained in the papers, organic papers. There is no generalizations for 11-dimensional supergravities because there is no dilaton.
But I'm saying that with this generalized type 2B can be also obtained from the 11th dimension without introducing
The comparison is when you lifting up the type 3 supergravities, so the generalization should vanish. I mean, this capital I should vanish. While you lifting up
there is something called the massive dimension reduction. I don't know if this massive. You're using some kind of push-ups rule, right?
Yeah. General visualizations were provided in these papers. I don't know how they define some general visualization, but I just followed the transformation rules.
You start to construct the supergravity something correspondence, but in the end you arrive at the generalized supergravity and correspondence. My question is the generalized supergravity is the key of the correspondence, or it's not necessarily important? Or?
Yeah, I think that's okay. So now we know the general results by Kali and Linus. So if we start from the initial strings, general supergravity should appear. So this is the result of this paper. So we inevitably encounter the general supergravity. So I think that this result is based on the general. So anyway, general supergravity is also related to the initial strings now.
What divide this from someone in category constraint?
out, sonority deduction should be replaced by generalized one. Yeah, because this is a general application of string service. How? Yeah. That is
maybe you could change the
organization.
Usually just schedule on string and then you can do a few different answer. How do we get to the how do we get this from string to this generalized type to be supervised?
So the plan is that if you just make sure what's curve bending.
In the curve
bending.
Oh.
And impose Kappa-Symmetry image. So these equations which follow from those.
So you can
but that doesn't mean this background is a good, defines a good control. It does not yet mean. It means it's clear. The sigma on the scale variant will not be one.
So it's may not be obtained from the same data function.
Yes. So there is no. It's not clear that there is a stress term which is traced. That's it. What is true is that stress term it's integrated over surface, the measure surface is zero. But when it's traced, any extra calculator.
You believe that will be the case, or
no? These are more general equations. So these background
this is just a consistent with the classical level.
Yes, classically consistent, but may not define proper consistency. But can you show your last transparency? So if I understand, so in a abelian case, the claim would be that so these backgrounds, abelian are matrices, because the backgrounds which solve usual type of equation, but one could say that the reason for that is because they can be mapped by PDFs to by usual abelian PDFs to backgrounds which solve usual type of equation. So the ground equation is invariant under usual T realities. So in these abelian matrices cases, examples like William of the Senex, TST, transformation of usual ATS satisfied. It looks like in all other cases also. This is true. While in non-abelian case, what looks like the general picture is that you have solution with generalized equations. You do formal T-duality or in Dirac. You can map it to solution of proper equation. Now, the Dirac the solution which you will get of proper type of equation which will have Dirac which is linear in dynamic direction. So that means this T-duality cannot be reversed. So that's what we call the generalized T-duality. So it looks like when in non-abelian case there is always this generalized T-duality which allows you to map the solution of usual. So that's good. But there should be more intrinsic reason for that. One probably can try to see how it works. Why for abelian matrix, which is A times B, as you discussed, there is a way to introduce proper coordinates in your life.
We have a coffee break until 3:20.
应该是其实没有注意，应该是。
其实我刚才有看了一下那个就是 spinning block 那个 stress fit 上最后有一个有在那边。Yeah. Right. So basically, the shadow form is shoot for
最后有一个4张。
Yeah, 那之前他是 right, that's 3 point, that's all good. 3 point.这个 matrix 这你有扣过。Right， 然后可是就是说可以怎么，或者说你可以怎么 package 这些 appropriate 的 derivative。那我在想，其实我们就是在 shoot 这个东西，其实就是应该是对应到说像在 spin 的 setup 的时候的发问题。Right， 其实就是真的拿到 right， 那 structure 最后是 movement 的 structure 这个样子。就是说我们 join 在OK， 那512就是说会有不同的 index， 它就这个是包括所有里面的 exchange channel 都已经include在里面。对，这个东西是讲的，这个东西是讲的。那这里就是要看针对说特定的这个特定的一个 exchange channel 做一个改写的，特别一个 symmetry traces 的这个 exchange channel 做改写。那所以说这个东西就是当我们把这 tensor structure 展开的时候，这 tensor structure 有时候是应该对应这里它的 inner product， 它的 tensor product 之后，然后你把它 decompose 成 irreducible representation 之后会得到的这儿，所以说你会有multiple number of 怎么讲？你会有 multiple number of spin。
Are you interested in going to Taipei tomorrow evening? Then you guys, if you feel you're going, then.
Thank you for the invitation. So I see.
Yeah, so we don't want to Kentaro and maybe Terashima-san.
I think they are all going back.
So Kentaro going back Saturday.
I see.
And I think Kono-san also going back. I don't know about Terashima.
I see.
Yeah, so if like 3 or 4 people, and then
Sure.
So share a cap. Okay, then I email you guys this evening, and so if you then we can have a dinner, and then after that you can, it makes sense that if you get a train back later, then you can share a cab back to the hotel as well. Okay, that's my side as well.
Thank you very much.
Okay, so let me do something this evening. Maybe arrange something today. Let you know. Yeah, so basically, right, so
Yeah, I think that's something we can 如果说做 screen of this person we should shoot for， 但是它 difficult， 它的点应该是说，比如说这个东西，对，应该是变成说 ，yeah， 就说如果是因为看我们刚才之前看到说，如果说有 space time spin 的时候 ，right， bulk 有 spin 的时候，就是用那个包括每圈 internal exchange 有 spin 的时候，你要把它 replace 成说 ADS signal cover derivative，right？ 那但是所以说可以想象说，你 boundary 的，也就是说你这个 boundary 有 spin 的时候，这些你应该有办法把它写成像是一个 cover derivative 在一边，但是 when you take a limit to the boundary， 然后它 reduce 成像这些combination 在 right and then 比如说跟他们那些，你说是所以比如说像我们这里面，后来就是有很写 ，yeah it's basically you should come from the combination yeah the propagator 对，但是它有一个 tensor free 的一个可以看出来。你是说上面有上次有一个是 general， 对啊，或者它有一个人绝对right， 但是它有一些 derivative， 这就是比如说加在这个形象。Right. It's basically something like that. 哦，他之前我没看到那个后面，之前的那个一个圈的等等。OK， 这是它的 index representation，W 是它的 polarization factor， 所以像这样的一个 differential derivative process， 而且你仔细看一下，啊，对啊，它这个东西你如果 compare 跟它那个 EO 的话，基本上这样的东西。As it should, and the point is that you really just rewriting the formula. 因为你最后这些有 tensor structure 其实是因为 k 作用在这些 tensor free 的 tensor structure. So we can, you guys should try to extract that yourself. 不会很难，但是 we should figure out what goes to what, right? If all things make sense 的话。Right. 我回去的时候会看一下这边的东西。我觉得我都不知道为什么就是拿了油就这样我算过，就拿油另外就借他来看，借他的带油就好，因为你自己要选东西。昨天那个这些什么绑的呀，这些什么绑的，先这个数量直接有就好了，没有差。我一直拿油，如果你要把它看成东西的话，就直接拿油。它怎么来了以后，就如果你要算新东西，差不多这样。如果要算新东西，就先拿，就是别人的有一点臭别人的有一点。对啊，不可能总会把书读完，然后再做研究，那就错了。这本来就大家都会这样做。因为我以前做在那个交大做那个别的，就别人的招生我就跳着做，跳着讲。或者你要做直接放在这里走。大概就在那里。我那边后来有一个漂亮，因为他本来没有的阿克上去，没有只有在阿克去。结果他2月的话，把他丢到Phoenix Bay去，然后就把我就那种超报警没版本，但是那一条都是撕裂的。
跟你后来就没有，就是你在
没有，可是这个是有个段落，就是到这个段落就可以，这个有一个小，这没有忘，这是我音乐。
你可以申请啊。
他等下要导音，对吧？
你可以申请导音，你可以申请。OK 了。
我在大学都拼音，
还有今年
说不上。
对，今年搞不好就可以直接。
我现在的时间已经不足，所以我不可能这几个月就全部把音乐全部弄完。
但有这个就够了。
我这个可以，这个学期好像我没有做古典书写，这个学期不错，相较于申请没有的时候，如果你们
对完全没有的是，
所以就这个大概这个我大概做1年，大3的时候看到，
然后做到大4，
就3下跟4上，
所以就等于你做完然后一个段落以后就来学校了，
就搞这个。
什么叫做就是
没有，我以前跟我没有考虑，我以前只是觉得这个好玩，
真的没有想过。
对，跟这边眼光比较广，眼界比较广。因为我如果大学认真搞研，搞不好就没有，我搞不好根本没有来台大，从来没有遇到过。然后他说累的那个只有失业而已，就关掉了。他没跟我讲，他没跟我讲，是啊，我不知道。他们都跑掉了。然后去吃啊？
我还好，
然后要跟我去喝饮料。
今天在干嘛？有，我最近就是控制热量非常严谨。
你是之前吃胖了？吃胖。
对，所以说你只要搭第一次就开始赶快用，要不然你根本用不完。
后期是没有用。
对啊。
说就是后期这样的，上车。
对。都没有用，一次也只能用。
这好吃吗？好吃。好，我去拿。
I stay on there, I probably now stay on there. usually my wife teaches me
就是我那个手，就是我那个手机那个，那个手机上，然后那个。
We'll have a second talk. Okay, so we will have our second talk in the afternoon, given by Professor Tony Lee from the National Taiwan Normal University.
Yeah, first would like to thank the organizers for giving the chance to give the talk here. So today I would like to talk about my recent work, relative entropy and ocean coverage, with my collaborator Paul Lee. Okay. So I think this year is the 20th anniversary of ADS-CFT correspondence. And in the past 20 years, actually, we encountered many good, I think, interesting and very inspiring phenomena. And I think the most important thing for this success is because we usually have another way to look in the old things we are getting used to. So, for example, we think we know much about the quantum field theory, but when we look from the gravity, we find we actually get more understanding about the quantum field theory. So similarly, recently, they are more and more emphasized. Probably you can look into the gravity and the quantum field theory in a more general sense than many body system from the quantum information point of view. Okay. So and the one key ingredient to link three fields together is the entanglement. And actually, original people, only people in quantum information theory started entanglement. But since 10 years ago, the Lee and Takanagi proposed the nice formula to calculate entanglement entropy in the context of ADS-CFT correspondence. We now get more and more handle to understand the important role played by the entanglement. For example, there is a nice interpretation of the EPR pair in the gravity, which are supposed to be the wormhole. And then we know that the quantum gravity maybe have some, in some sense, related to the quantum information. And also, from the quantum information point of view, the original many-body system actually can understand some kind of tensor network of local unitary operation. So we have some operational definition of the many-body state. So this is also important progress. And today, I would like to talk about a small piece of our work, which basically looking into the ADS-CFT or the gravity part from the quantum information point of view. And the motivation is like this. So suppose in initial stage, when we talk about interaction, we organize the interaction usually by symmetry principle. We either impose global symmetry or we impose gap symmetry, then we know how to write down the interaction by symmetry principle. And we want to understand if there is a possibility we can even go beyond this universal principle, and we can have some constraint on the possible interaction. So for example, usually we will say that we probably have some unitarity constraint, or in some sense, in modular sense, we want to understand if we add some interaction, if this interaction is the there's a UV convention for this interaction. However, this is a very general statement, and usually we don't know how to make this statement manifest. Okay, so now there's a new angle we can actually look into this unitarity constraint, which is a new angle we can consider some quantum information inequality. And this basically from this inequality, we can constrain some possible interaction in the CFT side. And then through the ADS-CFT correspondence, in fact, we are actually constrain some interaction in the back gravity side. And I think in the old days, the terminology called swap-length means that there are some interactions which are not natural, which are pathology, and you should just remove them out of the interaction in the space of your theory. So this is called a swap-length. And we find that actually we can do this, okay? And so I just have one page to summary ADS-CFT, which the content ingredient I want to use in the later on. So the duality actually, in some sense, at least only in the kinematic level, is organized by symmetry principle. Basically, we have on both sides we have the same conformal symmetry, and using this conformal symmetry, we can organize spectrum, and even we can organize the interactions. So, for example, in this talk, I will focus on the fermion interaction. So the simplest example is that if I have the Planck fermion field with fermion mass m, then this will due to a fermion operator which have the conformal dimension related to this. L is the ADS radius. However, this statement did not tell you what kind of interaction you should include in the back side in order to reproduce the necessary quantum CFT result. Okay, and also we know that the radial direction in the back side actually plays the role as the RG flow direction. Okay, and one more information is that usually when we solve the Bach equation of motion, for example, we solve the Bach equation of motion for fermion or for scalar. Actually, there are two integration constants, and each integration constant corresponds to either normalizable mode or non-normalizable mode. And usually we interpret the non-normalizable mode of the Bach field as the source for your boundary theory, and the normalizable mode will be the wave. So if you are in a linear response regime, this the ratio between the wave and the source will give you the transport coefficient. Okay, so basically this is the necessary ingredient I will use in this talk. And more specifically, this actually what I will going to focus on this talk. Actually, we want to understand if this kind of interaction is pathological from quantum information point of view, or not in the CFT side. So basically, this is the so-called torsion or contortion. So once you have the fermion, and then you couple to gravity, the natural ingredient, you need to introduce torsion, because there is a possibility the actual current of the fermion will couple to the torsion. Okay, so and you can ask the question why usually we don't consider torsion in the ADS-CFT context, because as we will show, you can only see torsion in the second order perturbation of Einstein equation. So most of the time we are only react once to the Bach matrix by introducing the fermion matrix. So if you don't go to the second order, actually, you are not necessary to introduce torsion. But in this talk, actually, my work is quite simple. And then the last talk in this afternoon, my talk is simply just to reinterpret how to solve the second order of Einstein equation with torsion and then reinterpret in the CFT language. Okay. And in the CFT side, we are actually in this scenario. I will turn on actually formula operator, and then this formula operator will then drive in for the RG flow. But at the same time, I also require this operator have non-zero value. And as you can see, I have introduced the volume integration to emphasize I only consider zero mole in this case. So I only consider turn on the zero mole formula operator with non-zero mole value. And in this setup, I want to consider the entanglement change. Okay, I want to consider how the entanglement entropy will change under this perturbation. Okay, so I review a little bit about entanglement entropy. So basically, entanglement entropy actually is considered a region, and if I have a quantum state, the quantum state, usually the ground state, is a pure state, and then I trace out the degree of freedom outside the region A, then I get a mixed state which is characterized by the reduced density matrix. And then you can calculate for Riemann entropy from this reduced density matrix and then get an entanglement entropy. So entanglement entropy actually is characterized the quantities of the state. So if your state is just a product state, then you will get no entanglement entropy. So the product state in some sense can approximate the classical sense. So if you have a non-trivial entanglement inside your ground state, then this ground state will be quantum. So if you have more entanglement, actually it's more quantum of this state, and that means it's more difficult to approximate by the mean field approximation. Okay, and especially only the entanglement between the region A and its complement. Okay, and there are many known facts about this entanglement, especially for the many-body system. And you can lay the general folklore saying that if you consider local theory and you calculate the ground state, then you calculate the ground state, the entanglement entropy for the ground state, and this ground entropy will obey the area law. Means that most of the entanglement are caused by the short distance pair. Okay. So on the other hand, you have something beyond the area law, means that you have long distance entanglement, which in the condensed matter system was called a topological order. So if you don't have topological order, then usually you will obey the area law. Okay. And besides, because entanglement entropy is a convex quantity, so it will obey many inequality. Actually, infinite number of inequality should be obeyed by this entanglement entropy. So the simplest and the most important one is so-called strong subactivity. So you will have A and B region, you calculate entanglement entropy associated with each region, and then they should satisfy this kind of some kind of triangle inequality. Okay, so this is important. So it's true for any unitary theory. So if this inequality is valid, means the series have no unit completion. And then comes this Rui-Takahashi formula. So basically, the entanglement entropy for quantum field theory is very difficult to calculate because you have infinite number of degree freedom. And the most generic trick is to use replica and in the framework of path integral. Also, in the CFT, especially in 1.1 CFT, you can also treat this entanglement entropy as the partition function in the presence of the twist operator. Okay, then we can get more intuitive understanding about this quantity. So basically, this statement of the Rui-Takahashi formula is saying that if I have the region A, then the entanglement entropy associated with region A actually is calculated by this formula. So the area of gamma A is the minima surface, cover the region A, okay, and then divided by the 4GN. Okay, this will be the entanglement entropy. And this formula, since proposed 10 years ago, has been tested by many different scenarios, and I think for the moment, everything is consistent with our understanding. So the nice things about this geometric realization is that, for example, this formula, this strong subactivity, actually, you want to prove in the field theory side, it's very difficult but you can prove by drawing diagram using Takagi formula. So basically, you can, from this you can see that the SA plus SB, you can replace this length by this interpretation. Then this length will be greater than this one because this is the minimal surface for A, B, C region. And this is supposed to be larger than this. Similar for this length to be larger than this one. So in this sense, it's very easy to calculate, to obtain this kind of inequality. And then there are people, they try to generate this kind of consideration, and you can get more and more inequality by putting more and more regions. Okay. And also there are important inequality like this. For example, if I have the black hole inside the boundary, actually is the finite temperature theory. Then in this case, the SA will not be equal to SB. This equality only holds if your underlying state is the pure state. Once you consider mixed state, then the A region entanglement entropy will not be the same as the B region entanglement entropy. And in this case, geometrically it's very easy to understand because if I have I have this region, but I have a black hole, then for this region, the minimal surface will be interpreted as this one. But for this complement region, this SB region, the minimal surface may be associated with this one. Okay, so the entropy will not be different because there is a black hole inside it. Okay. However, in this talk, I will consider a particular type of information inequality which are related to comparing the nearby state over region A. So more specifically, I will calculate the relative entropy of two reduced density matrix over region A. Okay. So this quantity basically just compares these two states. And I will calculate this quantity holographically. And then the requirement for this quantity to satisfy. And we will see what the constraint from this requirement. So basically, the relative entropy measures distance between the two states. So its definition is like this. You have two reduced density matrices, and then they will be related to this one. Their definition is like this. Okay. And basically, information-wise, it tells you what is the error due to the noise. Then you can compare the information you want to send and the one that contaminated by the noise. There will be the difference. So this quantity, by contraction, is always positive. It's not negative. Okay, because it's the distance of two states, and it's the error, how much error you made due to the noise. So it's always a positive quantity. And also monotonic means that if I have two regions, A and B, and if this B region is larger than A, then comparing the reduced density matrix, the relative entropy should satisfy this kind of constraint. Okay. And for example, you can understand what the significance by requiring the positivity. This is the one example. The example is that you can consider a thermal state. Okay. So for example, sigma is the thermal state, and then you deviate from the thermal state means that you deviate away from thermal equilibrium, and you generate a new state. Then you find that the relative entropy actually calculates the difference of the free energy. Okay, and because this F sigma is the free energy for the equilibrium state, then any deviation should be positive. Okay, so the positivity of the relative entropy actually is simply just saying that in this case it's the requirement of second law of thermodynamics. Okay, so yeah.
First line, the definition of second term is the lower sigma. The first line, the definition for relative entropy.
Which?
The first equation, first line.
Yeah.
Second term, is that the trace sigma log sigma?
No, it's right. It's the right one.
But in the third line, it seems it's antisymmetric with respect to change of rho and sigma.
Yeah, it's anti-symmetric.
Apparent one.
You can check. It's not symmetric. Yeah. If you change sigma and rho, you can get difference. Okay. It's not a symmetric quantity. Otherwise, if low sigma is positive, I would expect sigma rho to be negative, but it's not the case. Okay. So, And I was confused before. No, they don't call it that. so probably it's a stupid name, but I think in the quantum information society they have another name which is not like validity. Yeah, I forgot the people's name. So in this case, however, this is not symmetric.
So it's an ADS-CFT proposal for computing this one.
Yeah, this one I want to talk about. Yeah. So basically, so I just want to let you know that the positivity of relative entropy actually have physical significance. For example, in this case, in the second law of thermodynamics, that's important. Okay. And then, actually, once we define this, we want to know how to calculate it holographically. But before doing that, I need to introduce another quantity, is so-called modular Hamiltonian or entanglement Hamiltonian. Basically, it's just to rewrite the state, the reduced density matrix in terms of some Hamiltonian operator. Okay, so basically, just take log, and with a minus sign, then you get an entanglement Hamiltonian or modular Hamiltonian. And its spectrum is called entanglement spectrum. And this entanglement spectrum actually is more refined than the entanglement entropy, because entanglement entropy is just some combination of the entanglement spectrum. So the entanglement spectrum actually can give you more information about your ground state. So for example, in some sense, the entanglement spectrum will encode the topological property of your quantum state. If your quantum state has topological order, then it will reflect in the gapless. You will see the entanglement spectrum will be gapless. So this is the important quantity. However, in general, the entanglement Hamiltonian is not local, and it's unknown. However, there is a situation in which you know what is the form of the entanglement Hamiltonian. When this region A is light-like or sphere, and you are considered Coulomb field theory. Then in this case, for example, in the sphere case, the entanglement Hamiltonian is related to the energy density in this way. And why we have this kind of nice formula, because we can map this sphere into a rendered space by conformal transformation. And we already know that the entanglement Hamiltonian or modular Hamiltonian for the rendered space is simply the energy density, because it's driven the modular flow. And then once you know this, and then you map back, you get this form for the sphere. So for the moment, and in the rest of talk, I will only consider the entanglement on the sphere. Okay, and also I will consider CFT. And then, based on this, we can rewrite the relative entropy in terms of modular Hamiltonian and the entanglement entropy. So basically, you can check this relative entropy actually can rewrite as the difference of the web of the modular Hamiltonian. The definition is here, you can check. And then minus the change of your entanglement entropy over region A. Okay, so actually, in this case, we always use sigma A as a reference state. And so you can check the size is okay. And we will be more simpler, even simpler. In this case, we only consider two nearby states. Means that the excited state rho would be just a very small deviate from the sigma. And because the entanglement entropy is a convex quantity, so at the first order, immediately you will find that at first order, relative entropy should be 0. And in this case, you find that the entanglement entropy will satisfy this kind of relation. Okay, this is called the first law of the entanglement thermodynamics. Okay, so this equation is famous because it's just like the usual thermodynamics. And we know that many years ago, Marini, based on this Jacobson's proposal, he tried to redefine Einstein gravity from the first law of thermodynamics. So in fact, you can do the similar things. You have this first law, and then this first law, you can reinterpret actually this first law as kind of non-local representation of your linear Einstein equation. So you try to find out some good tensor which you can turn this non-local expression to local expression. Then you verify that actually this is statement equivalent to the linear Einstein equation in ADS background. Okay, and by this way, once we know the linear order, we can just recursively do this, and we can control Einstein gravity. So this the first order you already see is it gives you a nice result. Okay, and then we can go to the second order, and you find that in the second order, immediately you will find that the relative entropy will not be 0. If it continues to be 0, then it's just trivial. So the second order is not is 0. It's not 0. So in this second order, actually, you will hear the non-trivial information equality on your CFD or this deformation. Because as I said, we are compared two states, two nearby states. So any deformation away from the ground state will contain the dynamics of your theory. And if you have some requirement for some quantity to be non-zero or to be positive, then you will find that this actually contains your underlying dynamics. Okay, so the theory, one theory violating the equality is pathological. Okay, and also, so later, for example, if we turn on the scalar field in the box, and then you try to calculate the deformation of the ADS background, and then you will ask, using that, I calculate both the entanglement Hamiltonian and the change of the entanglement entropy. Then what is the constraint? Then the constraint actually gives you the unitarity bound for the scalar case. We know that for the box scalar field, there is a bound on the mass square. It's called a BF bound. Beyond the BF bound, it means that they will induce the instability of ADS space. Of course, the instability of ADS space recently is very subtle, so I refer to the old days understanding. Okay. So this was done first by these people. So in the box side, actually, you will ask why we have such kind of a bound at the second order. And actually, this bound what actually is equivalent to the positive energy condition. Okay, because in the first order, we solve the Einstein equation, and it's a linear order with solved by the first order Bach matrix. But when we go to the second order, the first order graviton will acting as a source to solve the second order of the graviton perturbation. Then in this sense, the first order actually will contribute a stress tensor to solve the graviton combined with the matter. And then you combine both, you actually will require the total energy to be positive in order to preserve the stability of ADS background. So this turns out in this paper, they show more explicitly in the covariant way by using Watt construction, using the construction method developed by Watt and his cooperator. They can show that actually this will be the case. Okay. However, in this paper, I only want to consider a specific case with Bach fermion coupled to the torsion gravity. Yeah. The reason that we seldom talk about torsion, and we have less understanding about torsion gravity. So probably we can use this kind of constraint to understand what the requirement will impose on this torsion gravity. Okay. So actually, if you read some review, actually the good review by the Hare and his cooperator, actually there are many people discuss torsion, even including Schrödinger. Schrödinger in the 1960s, he wrote a nice paper review the torsion gravity. And also we don't know much about quasi-local energy or energy condition of the torsion gravity. We have a local expert like Jim Nestor, and I think we consult him about this quasi-local energy condition. And actually, he said he's not so sure about when you consider torsion what we have. And also interesting that, it's interesting to see what the information causality considered before with Taylor in the ADS-CFT context. So the simplest torsion gravity is Einstein-Cartan torsion gravity. I will just give you the definition in the next page. So we will consider Einstein-Cartan torsion gravity. And the reason why most of the time when you study general relativity, you never talk about torsion, because macroscopically, the spin of the fermion will be averaged out. So without the average spin, you don't need the torsion. But if we consider microscopic theory, we always have the microscopic fermion, and then the source, the spin will be it's called the spin will induce so-called spin energy spin stress tensor, and this stress tensor will couple the torsion. Yeah. So the torsion gravity actually they had a nice review by these people, including June Nesbitt. And actually torsion is defined by this anti-symmetric part of the crystal symbol. Once you include torsion, then your crystal symbol will no longer be symmetric. However, you still need to satisfy the metricity condition so that locally you obey the equivalence principle. So this is an important constraint. It makes this whole thing complicated. And the simplest gravity action, the Einstein contact actually is similar to the Einstein action, because the only thing changed is that your convection, alpha convection now is changed. Okay. And also, once you introduce fermion, the fermion will cover. We will write down the Dirac equation, Dirac action for fermion. So either in the same form as the usual Dirac action, except the covariant derivative now contain the part of torsion. So this omega theta is still writing in terms of Riemannian convection, and the additional part we see the contortion we define soon. So later additional contortion part will cover to the fermion. And the contortion actually just symmetrize or anti-symmetrize the first two index. Okay, so this is a contortion, and then the Lagrange for the fermion, it can be written as the usual Dirac Lagrange plus something new. So here, eta t is the covering we introduced on purpose, because naively we say eta t equals to 1. If you don't care, then naively you replace the usual covariant derivative by the new covariant derivative. You will always write eta t equals to 1. Okay, but we will simplify. We will introduce this covering to see what the role of this eta t will play in the information inequality. And then the new interaction is between this contortion and this new 3 index tensor. This new 3 index tensor is the definition like this. So it's called a spin angular momentum tensor. And if you solve it, if you calculate by the definition, you find that this spin angular momentum tensor is nothing but the actual current. Okay. So this interaction actually tell you there is a covering between the actual current and contortion. Okay. And so this is a new ingredient once you introduce torsion covering to the fermion. So in some sense, we would like to calculate relative entropy for the Horvath field of this torsion gravity. And we in some sense, we will calculate the second order, we will solve the second order equation of motion. Okay. And the expansion parameter is the Newton constant, or this delta lambda. Okay. So this background is due to turning on the deformation, because I have the turn on fermion, and this fermion will be going to be a formula operator. So in some sense, I just turn on the fermion. This is quite different from the earlier discussion on this relative entropy, because most of the time they just turn off the non-normalizable mode. So they only consider the normalizable mode. So they just consider the excited state in the same theory. But once I turn on this deformation, it means that I compare the state for different theory, because this deformation will just evolve your theory away from the fixed point. So I will actually consider the state in different theory. Okay, but I will consider only nearby the fixed point. So the Hilbert space, I assume, will not change a lot. Okay. And also in this sense, the relative entropy should be positive. As we know that in the second order, then the entanglement, the marginal Hamiltonian is 0. So the relative entropy is just, in some sense, the negative of the change of entanglement entropy. So the positivity of relative entropy, it turns out to say that the entanglement entropy should be monotonic decay. decrease under RT flow. So in some sense, this is a statement like the C theory you usually have. Okay, in C theory, you count in the degree of freedom, but in this sense, you count in the entanglement, which also associated with number of degree of freedom. So if your number of degree is decreasing, you expect that your entanglement also decreasing. So it's a very natural expectation you should have this kind of positivity condition. However, we found that in the fermion case, if we didn't turn on the web, actually the relative entropy is just trivial. So in order to make this information inequality not trivial, actually, we also need to turn on the web of the zero mode. And then it's just simple, just everything from now is just straightforward. We just write down the Fourier equation in the perturbative sense. So we have the zeroth order, the first order, and then second order equation of motion. And to do this, actually, we just rewrite everything in terms of Riemannian connection and separate torsion as a new method field. So when you see this, it's actually saying that this is the usual Einstein equation, and this is the usual Dirac equation. And you see, then the first order matter, zeroth order matter will contribute to solve the first order metric perturbation. But up to this order, you don't see any torsion condition comes in. So here there's something here, but this solving for the next order fermion. So for the Einstein equation, you don't see any torsion covering comes in. So actually, at this order, you don't need to have torsion. So this is why in usual ADA CFT content, we don't discuss torsion because we seldom go beyond the second order perturbation. Okay. However, in the second order perturbation, the torsion will come in. So you see that the source actually contain the spin angular momentum tensor. So the torsion will come in at the second order. So at this order, you should take care of the torsion contribution. So once we solve the perturbative equation and we get the metric, then we just do two things. The first thing is we using the new metric to calculate our graph straight tensor. And then using the straight tensor, we can calculate modular Hamiltonian. And it turns out only first order metric will give you the modular Hamiltonian because the second order metric is automatically give you the zero straight tensor because the straight tensor have need to pick up a right pole in the Feynman-Graham expansion, and the higher order actually will not contribute to the straight tensor. So you will only get the straight tensor at the first order contribution. And in the usual sense, it is a black hole mass, as you want to consider. So, and then we use the RT formula to calculate entanglement entropy. But because there is no second order, there is no second order modular Hamiltonian, so the second order relative entropy simply just evaluate the change of entanglement. And of course, we in some sense need to find a minimum geodesic in the perturbative matrix. So it's the equation of motion for the second order minimum geodesic is quite evolved. So we will use a trick test because the first order is also exact solution is the saddle point. So in some sense, we can calculate the second order by just solving the minima surface as first order up to the second order, and then we evaluate the minimum area according to the second order metric. Then we get the entanglement entropy change up to the second order with all the correction captured. And then this is the result. So the result is because we are considering zero mode, so everything is so simple. So actually you can find the exact solution. So basically we have two integration constants. One is called alpha, and the other one called beta. And this is the change of the metric. And the alpha actually can be understood as due to the source, which is a covering constant. And the beta is due to the web. And also you can calculate straight tensor, holographic straight tensor. And you will see that holographic straight tensor is look like this. And immediately you find out this equation of state is not conformal equation of state. So that means once we introduce the deformation, you are away from a fixed point, so you will lose the conformal symmetry. Okay. However, even at this order, even if it's not conformal, the relative entropy is still finished. You can calculate the modular Hamiltonian, and then you find it, and then calculate the first order change of the entanglement entropy, they match. So
the relative entropy is still 0 even it's not a common fixed point anymore. And then we can ask if you don't want to calculate the 0 mode, you find that it's difficult to get a closed form in that solution. And then you have also T and X everywhere. So it's not clear at this moment, can we generate to more non-zero mode case. So it becomes more evolved and more definite conclusion we can get. Okay, so we will just restrict to the zero mode case. Then even to the second order, we still got the exact solution. And then you have more complicated stuff. And then in this case, the eta T comes in. Okay, eta T is the actual cover, actual current, and the torsion cover. So the torsion will come in the second order solution. And if you calculate the relative entropy, which is simply just a change of the integral entropy, you get this kind of relative entropy. So you will see that the relative entropy at each order actually in proportion to alpha times beta. So if alpha and beta either one is 0, then the relative entropy is just trivial, as I just claimed before. On the other hand, if this is not 0, then the constraint for this quantity to be positive. And you find that the free strange constraint comes out. It means that the mass squared times L squared needs to be greater than this quantity. And unlike the scalar case, the scalar mass square actually have the VF bond. But for the fermion, actually we don't have VF bond. So in the usual sense, you can have any fermion mass, it will not cause instability of ADS space. So if we impose this bond, it means that if eta T not equal to 0, it means that there is some new mass bond comes out. But that's very strange. I don't know how to understand this point. So the simplest way is just to set eta T equal to 0. Then you don't have bond anymore. So this non-trivial bond, the simplest solution, or simplest statement, we can say that we can just set eta to 0. Then this bond will automatically satisfied. Yeah. Otherwise, you have a non-trivial bond of the mass squared. Okay. Of course, this is not a usual type deformation because we also turn on a web, and this web actually is a fermion web, so naively break the Lorentz symmetry. So there is some implication here. So I try not to understand this. Okay. So if we allow this web to be there, then we find out actually the information inequality disfavor the actual current torsion cover. And so some of the point I was just mentioning, as I said, unlike scalar, we don't have VF bond. So the mass bond coming from information inequality is quite strange. Okay. Also, unlike pre-study, we actually invariant relative entropy is not in the same theory, but along the RG flow. So this is also a new point. However, if we just do it from that point of view, actually we get the same conclusion. In the back point of view, we just solve Einstein equation. So at the second order, we get some quasi-local energy. That quasi-local energy should obey some energy condition. Otherwise, you will get some kind of, otherwise you don't guarantee the paradigm energy 0. Okay, so we require a quasi-energy condition. Okay. However, we are not so sure if this is the same as the usual quasi-local energy. For example, I think there are many different schools define the quasi-local energy. And the one popular school adopted by the string series is the school by the Watt and its cooperator. And they have some construction to control the quasi-local energy. So basically, the construction is quite intuitive. It's basically coming from a boundary variation of the action, and also you will impose some isometry. Then this quasi-local energy, the change of quasi-local energy actually is related to this boundary variation, this symplectic form. And then from this symplectic form, you can derive quasi-local energy. And for in the concept of the Einstein gravity, actually, some previous study by Remstorm and his cooperator actually showed that the relative entropy actually is equivalent to quasi-local energy. So the positivity of the relative entropy actually the same as quasi-local energy to be positive. But we are not so sure if this is also the case for the torsion gravity. So actually we are currently just working on this question. Okay. However, our result also motivated we should have more study on the information causality on the RG flow. And actually there's a very recent paper by Zhou Yang. Actually, he not consider RG flow, but he considered rain entropy, and you can change the rain index. And the change of this rain index also require this relative entropy to be positive, or this rain entropy to be positive. And he find that using this, he can derive some bound on the central charge of superconductor field theory. So for example, they can derive the so-called Hofmann-Singer bound for the superconductor field theory. So actually, this just the message saying that if we consider the information causality, we actually can go beyond the symmetry principle to constrain the interaction like what we found here. So actually, all this indicate that they should have an interesting interplay between quantum field theory, gravity, and the quantum information science. Thanks.
Question? Look to me your interpretation about setting the coupling of the torsion field theory. I think it is interesting the contribution from the torsion should be too big compared to the contribution from the mass. So it's more likely that the function of the sign of the torsion which can appear in the field.
Yeah.
Rather than saying that it should be zero.
So we say it's disfavored. We don't, in the paper, we don't want to say it should set to zero.
Okay.
Yeah.
It's not even okay. Cut out some part of moduli space.
Yeah, it's actually we cut out some part of modular space according to locality. Yeah, by studying the specific interaction. Of course, there are many interactions you can think about. The point is that this interaction cannot be pinned down in the usual dictionary or ADS-CFT correspondence. Yeah, so it's not so clear we should include that or not. Yeah.
And this would be, should I agree with it?
Yeah, sure, I think so. I hope. But the point is that there is much less understanding about the quasi-local energy condition in the torsion graph. But naively, we can just separate torsion from crystal simple. And then this torsion will be a new matter field. And in that case, I think the usual particle energy condition will be expected to also hold also.
Yeah.
So I would expect that once we finish that speculation, we will get the same condition.
So usually when you couple when your fermion is charged, then this the charge of your fermion will be the coupling in this covariance field.
Yeah.
So in the torsion case, the coupling of the torsion, the fermion field, there's also a coupling term.
Yes.
The coupling term is independent from the charge of this fermion.
Yeah, this is independent because it's coupled to the torsion. The charge you mentioned probably coupled to some E1 on our billion gauge field.
So,
but here we didn't introduce any charge actually. Something in the global, we don't introduce a gauge field.
So in this case, you don't have any other constraint for that charge.
Yes.
So that couple.
You mean
is it that eta t?
Eta t is the covering constant. We introduced on purpose is to say actually we have control. We also have
eventually say to be zero in order to have.
Naively, because we calculate and then at the beginning we set eta t equal to 1. You naively would do that. You go to this review by Hayes group. They actually didn't specify the covering constant eta t. They just simply set equal to 1. And then you find some strange constraint, and then you will suspect that this constraint must due to this covering. So we reset this covering and we find that actually it really appears on the constraint. So then you know that the strange constraint coming from turn on this covering. Otherwise, naively, we will simply just turn on the covering because if torsion must create some law to interacting with matter, it should be interacted through the actual current. and naively we set it equal to 1. Because then in this case, the fermion have the equal footing as the metric coupled to the connection. Yeah. Otherwise, you set equal eta p not equal to 1. It means that the interaction of graviton coupled to a connection will be different from the fermion coupled to a connection. They would not be the same. So in some sense, you say eta p equal to 0. In some sense, the equivalence principle are broken. You can say that because then the gravity can tell difference. Once you introduce the torsion, the gravity can tell different. You couple to gravity or you couple to the formula. They will couple different.
Then in this case, do this so-called weak gravity conjecture still apply?
Yeah, in some sense, it's just tell you that you don't obey this positive energy condition. In some sense, the weak gravity conjecture was valid. Even I didn't introduce charge. Usually, weak gravity conjecture was introduced when you also have some U1 charge. Then they the constraint on the charge and mass ratio. But here, I didn't even consider the charge case. I only consider coupling to the torsion. So in this sense, it's kind of weak gravity conjecture. If we consider the eta p as some charge coupled to the torsion, then you don't want the charge to be too large.
Comments? No, let's thank Tony again.
Then if I set it, no. When I do the calculation, I separate the torsion from the reminder. But we don't have remind, their connection will, yeah, but remind connection will not obey the metricity. So if I want to discuss the equivalent I will not use the reminder connection, I will use the alpha. And then this, if I want to use alpha connection, when I write down the Dirac equation, I should expect I write down the Dirac equation before itself just in case. Already I'm using alpha connection. But if I take eta p equal to 0, means that I might, I just mean that couple to using the Riemannian connection, not the alpha. Then there is a difference between alpha and gravity. Equivalence yeah. So yeah, of course, I just you have different statements. If you are saying that I would say the metricity condition in some sense condition for so usually if you introduce a new power, you should always so if I now find that I cover the formula, I don't want to use this alpha connection, I just use the Riemannian connection. Means that the gravity and the formula they can cover different because there